These are the longest mega projects ever built. Stretching across continents and hostile terrain, these colossal structures took decades to complete, demanded revolutionary construction methods, and tested human endurance on an unprecedented scale. In this documentary, we explore how these massive projects were designed, why they took so long to build, and the extreme challenges engineers had to overcome to make the impossible finally stand. Beneath Biscayne Bay, hidden from the skyline that defines Miami's mega-project boom, the Port of Miami Tunnel represents one of the most complex and consequential infrastructure projects ever built in South Florida. The Port of Miami Tunnel was designed to directly connect Dodge Island, home to Port Miami, with the interstate highway system, creating a dedicated underground freight corridor between the port and Interstate 395 and Interstate 95. Before the tunnel, cargo trucks were forced to move through downtown Miami streets, creating chronic congestion, safety issues, and delays that constrained the port's growth. The tunnel fundamentally restructured how goods move through the city, making it a critical component of Miami's broader mega-project transformation. Planning for the tunnel began decades before construction, with serious development efforts accelerating in the early 2000s as Port Miami expanded into a major global cargo and cruise hub. Construction officially began in 2010, after years of environmental review, financing negotiations, and engineering studies. The project was delivered through a public-private partnership, an uncommon approach at the time for U.S. transportation megaprojects, involving the Florida Department of Transportation and a private concessionaire responsible for design, construction, financing, and long-term operation. The construction scope centered on two parallel tunnel tubes, each approximately 3,900 feet long, bored beneath Biscayne Bay. The tunnels were excavated using a massive tunnel boring machine specifically designed to operate in Miami's challenging geology, which consists of porous limestone, sand, and a high water table. The tunnel boring machine, weighing thousands of tons, was launched from Watson Island and advanced underwater toward Dodge Island, cutting through bedrock while simultaneously installing precast concrete liner segments to stabilize the tunnel walls. Excavation operations required continuous groundwater management and precise pressure control to prevent collapse or water intrusion. The tunnel alignment passed beneath active shipping channels, requiring careful coordination to avoid disrupting port operations and marine traffic. Spoil material removed during tunneling was transported and processed without interfering with surrounding urban and maritime infrastructure. In addition to the underwater tunnels, the project included extensive cut and cover construction on both ends. On Watson Island and Dodge Island, large access portals were excavated, requiring dewatering systems, retaining walls, and deep foundations to support the tunnel entrances. New roadway interchanges were built to connect the tunnel directly to I-395, eliminating truck traffic through surface streets in downtown Miami. Construction also included advanced ventilation buildings, fire suppression systems, emergency cross passages between tunnel tubes, and real-time monitoring systems. These safety features were essential to meet federal highway tunnel standards and ensure continuous operation in a hurricane-prone region. The tunnel was engineered to withstand storm surge, seismic forces, and long-term exposure to saltwater conditions. The project faced multiple technical and schedule challenges during construction. Delays occurred due to mechanical issues with the tunnel boring machine, groundwater infiltration events, and the complexity of working beneath an active port and bay. Despite these challenges, tunneling was completed in 2013, marking one of the most technically demanding phases of the project. Following structural completion, several years were dedicated to roadway finishing, systems installation, testing and commissioning, ventilation, lighting, traffic control, and emergency systems underwent extensive testing before the tunnel was open to traffic. The Port of Miami Tunnel officially opened in August 2014, completing a construction timeline of roughly 4 years. Within the context of Miami's biggest mega projects, the Port of Miami Tunnel stands apart from high-rise developments like Panorama Tower or Brickell City Center. Rather than reshaping the skyline, it reshaped the city's logistical foundation. By removing thousands of trucks per day from downtown streets, the tunnel enabled parallel megaprojects in residential, commercial, and cultural development to proceed without freight congestion limiting growth. Beneath the waters and roadways of Miami, the Port Miami deep dredge and tunnel projects reshaped both the marine and terrestrial access to one of the busiest cargo and cruise ports in the United States. These two interconnected mega projects required cutting-edge marine engineering, precision tunneling beneath a densely populated urban core, and rigorous coordination between federal, state, and local agencies to expand the port's capacity and streamline its logistics network. The Deep Dredge project aimed to deepen the port's main shipping channel from 42 feet to 50 feet, allowing for the accommodation of new Panamax-class vessels transiting through the expanded Panama Canal. To execute this, specialized dredging vessels were brought in, including cutter suction dredgers and trailing suction hopper dredgers, capable of removing millions of cubic yards of seabed material. The challenge lay not only in excavating to such depths, but doing so without disrupting sensitive marine habitats, port operations, or submerged utilities. Dredging operations were sequenced in phases, beginning with hydrographic surveys to precisely map the underwater topography. Blasting was employed in sections of dense limestone, with marine-safe explosives timed to avoid impact to sea life. The excavated material was carefully monitored and disposed of at authorized ocean disposal sites or used in beneficial reuse programs like beach renourishment. Environmental control measures included turbidity curtains and marine species observers aboard all vessels. Simultaneously, the Port Miami Tunnel project unfolded beneath Biscayne Bay. This initiative involved the construction of twin tubes running approximately 4,000 feet in length, connecting the MacArthur Causeway on Watson Island to Dodge Island, the heart of the port. The tunnels were designed to divert truck traffic from downtown Miami, enhancing safety and easing congestion. To construct these tunnels, a custom-built tunnel boring machine, nicknamed Harriet, was deployed. Weighing over 2,000 tons and spanning nearly 40 feet in diameter, the TBM was assembled in a launch pit on Watson Island and advanced through a limestone substrate beneath the bay. The tunneling process involved simultaneous excavation and installation of precast concrete segment rings, forming the tunnel lining. These segments were waterproofed and grouted in place, forming a watertight shell that could withstand hydrostatic pressures and resist intrusion from saline water. Tunneling beneath the bay demanded constant monitoring of groundwater pressure, cut-ahead torque, and soil composition. The TBM operated with an earth pressure balance system to stabilize the tunnel face and prevent collapse. The spoil removed from the tunnel was conveyed by belt system to the launch shaft and trucked off-site. Crews worked in rotating shifts, operating around the clock to maintain excavation rates and minimize disruption to the bay and surrounding infrastructure. Once the structural shell was completed, interior systems were installed, including ventilation fans, LED lighting, fire suppression systems, CCTV surveillance, and emergency egress walkways. A robust stormwater drainage system was also built into the tunnel floor to channel any water intrusion into sump pits and eject it via high-capacity pumps. Taken together, the Port Miami deep dredge and tunnel projects not only increased the capacity and efficiency of port operations, but demonstrated how complex marine and tunneling engineering solutions can be successfully executed in a high-stakes, environmentally sensitive, and logistically intense urban setting. South of Chicago's Loop, and directly east of Grant Park, one of the most ambitious and complex megaprojects ever proposed in the city, is planned not on open land, but above active rail infrastructure. One Central Chicago is a large-scale, long-term development proposal centered on constructing a massive transit-oriented platform over the Metra Electric Rail Yard near Soldier Field, redefining how Chicago approaches air rights development. The core of the One Central proposal is the construction of a multi-level structural deck spanning more than 30 acres of rail lines. This deck would serve as the foundation for an entirely new neighborhood, allowing vertical development to rise above existing transportation corridors without displacing them. The engineering challenge is central to the project, requiring heavy load-bearing caissons, vibration isolation systems, and phased construction that allows uninterrupted rail operations below. The project is structured around a new central transit hub, envisioned as one of the largest in the Midwest. The hub would integrate Metra electric trains, CTA bus services, potential future rail connections, and pedestrian and bicycle networks into a single, consolidated station. Transit infrastructure is planned as the first major construction phase, establishing the structural deck and station facilities before any private buildings rise above. One Central is approved conceptually as a multi-decade development, not a single construction effort. The full build-out is projected to extend into the 2040s, with individual phases dependent on financing, tenant demand, and infrastructure funding. Early construction would focus on the deck, transit facilities, and utility systems, a process expected to take several years before vertical development begins. The proposed scale places One Central among the largest megaprojects in Chicago history. At full build-out, the plan allows for millions of square feet of mixed-use development, including residential towers, office space, hotels, academic and research facilities, and cultural venues. Building heights would vary across phases, with some towers reaching high-rise and super-tall classifications, though final designs remain flexible. Infrastructure construction is the defining feature of the project. Beyond the deck itself, One Central requires new roadways, stormwater management systems, electrical substations, and telecommunications networks. Because the site sits between Lake Michigan and downtown, flood resilience and drainage engineering are critical components of the design. Elevated building pads and integrated water management systems are planned to address long-term climate risks. Unlike many Chicago megaprojects, One Central has not yet entered full construction. As of the mid-2020s, the project remains in advanced planning and approval stages, with negotiations focused on public-private partnerships, transit funding, and long-term governance. The project's viability is closely tied to securing funding for the transit hub, which is considered essential to unlocking the value of the surrounding development. The location gives the project strategic importance. It sits between the museum campus, McCormick Place, Soldier Field, and downtown, creating a potential bridge between Chicago's civic core and its convention and entertainment districts. The development would also reconnect neighborhoods long separated by rail infrastructure, using the deck as both a building platform and a public realm. From a construction sequencing standpoint, One Central differs from traditional real estate projects. No single building can proceed independently. Each phase depends on completion of shared structural and transit elements, making coordination and long-term scheduling central to the project's execution. This complexity places One Central closer to infrastructure megaprojects like transit expansions than conventional mixed-use developments.
Jordan Downs wasn't built to last, but it lasted. What began in the 1940s as temporary war worker housing in the heart of Watts evolved into one of Los Angeles's most recognized public housing projects. For decades, it stood as a symbol of neglect, of disinvestment, of the city's fractured promises. Now it's at the center of one of the largest and most complex urban redevelopments ever attempted in Southern California. This is the Jordan Downs redevelopment, a multi-phase billion-dollar megaproject that's rebuilding an entire neighborhood from the ground up. We're not talking about a simple renovation. This is full-scale urban reconstruction, replacing over 700 aging public housing units with a mixed-income community of more than 1,400 new homes, complete with parks, retail corridors, a new street grid, and state-of-the-art infrastructure. And all of it is happening while people still live there. That reality, redeveloping a live-in community without displacement, is what makes this project such a massive logistical and engineering challenge. Everything had to be phased. Crews couldn't just level the site and start fresh. Instead, new housing blocks were constructed in stages on available land, allowing families to relocate within the community as old units came down. That required intense coordination, not just in construction, but in utilities, access roads, and safety systems, all while keeping the neighborhood functioning. Before any new buildings could rise, the land itself had to be re-engineered. Jordan Downs sits on a former industrial site, contaminated from decades of adjacent manufacturing. That meant full environmental remediation, soil testing, removal of hazardous material, groundwater management, and installation of protective barriers. Engineers excavated tens of thousands of cubic yards of earth, replacing contaminated soil with engineered fill, compacted and monitored for stability. Next came infrastructure. The original Jordan Downs layout was a relic of mid-century planning. Isolated blocks with limited connectivity and almost no integration into the surrounding street grid. To fix that, the project involved installing an entirely new road network, complete with sidewalks, bike lanes, storm drains, and underground utilities. A major extension of Century Boulevard now runs through the site, connecting it to the broader Watts area and giving the community a direct arterial link to the rest of the city. Structurally, the new buildings are designed for both density and resilience. Wood frame over concrete podiums dominate the design, balancing cost efficiency with seismic durability. Each structure is engineered with fire suppression systems, earthquake-resistant framing, and energy-efficient insulation to meet California's Title 24 building codes. Sustainability was also baked in. Solar panels, drought-tolerant landscaping, and stormwater capture systems are integrated across the site. And unlike the original layout, the new Jordan Downs is being built with mixed-use development at its core. A central retail village is part of the plan, complete with grocery stores, cafes, and community-serving businesses. That required additional engineering for load-bearing slabs, commercial-grade ventilation, and enhanced utility access to support food service and retail operations. The project also includes new parkland, recreational facilities, and space for schools and job training centers, all of which had to be laid out on what was once a closed, fenced-off grid.
In the southeastern corridor of the United States, where infrastructure development often grapples with both dense urbanization and expansive wetlands, the construction of the Brightline high-speed rail line connecting Miami to Orlando represented a major engineering endeavor. This privately funded rail project was designed not only to introduce high-speed rail to Florida, but also to demonstrate the viability of higher-speed passenger rail service within existing and constrained right-of-way corridors. The execution of this project required a comprehensive integration of new track construction, upgrades to existing freight corridors, and the implementation of advanced signaling and safety systems. Initial site work commenced with a detailed geotechnical analysis of the entire corridor, which spanned over 200 miles. This included evaluating soil stability, drainage characteristics, and subsurface conditions, particularly through the swamp-prone regions of Central Florida. In areas where existing tracks were used, such as the Florida East Coast Railway corridor between Miami and Cocoa, crews had to reinforce subgrades, replace worn ballast, and realign curves to support sustained higher speeds. Track geometry was meticulously adjusted using specialized rail alignment equipment to ensure smooth transitions and compliance with Federal Railroad Administration safety criteria. For the new segment between Cocoa and Orlando, a greenfield corridor was constructed largely along the State Road 528 Expressway median. This presented its own suite of engineering challenges, notably the design and construction of elevated track sections and bridges over sensitive wetlands and stormwater retention zones. Precast concrete girder spans were transported and installed using massive mobile cranes to expedite assembly and minimize environmental impact. Track beds along this route were laid on compacted sub-ballast, topped with engineered ballast layers, ensuring long-term durability under the dynamic loads imposed by high-speed rail operations. The track system employed continuously welded rail, which was delivered in long segments to reduce the number of expansion joints and improve ride quality. Rail thermite welding teams were deployed to join these segments on site with strict quality control to ensure alignment and weld strength. Dual track configurations were introduced in several key sections to allow bi-directional travel and service flexibility, especially near the Orlando International Airport terminus. Stations were another significant component of the build. The MiamiCentral station, integrated into downtown Miami, required a complex vertical design solution involving multi-level platforms, elevated passenger concourses, and integrated commercial development. Structural steel framing supported concrete deck slabs, and the entire facility was constructed above active roadways and in proximity to other mass transit systems, necessitating rigorous coordination and sequencing of construction activities. Advanced signaling and communication systems were installed throughout the corridor, including positive train control, to ensure operational safety at high speeds. Grade crossings along the route were upgraded with quad gate systems, median separators, and enhanced warning devices to reduce the risk of vehicle-train interactions. Along the newer segments, full-grade separation was implemented via underpasses or overpasses. Beneath Chicago's streets, rivers, and neighborhoods lies one of the largest underground civil engineering systems ever built, a megaproject whose scale rivals any visible skyscraper or transit expansion in the city. The Tunnel and Reservoir Plan, commonly known as TARP or the Chicago Deep Tunnel, is a decades-long infrastructure program designed to control flooding, reduce sewer overflows, and protect regional waterways. The origins of TARP trace back to the mid-20th century when rapid urban growth combined stormwater and sewage into a single system that frequently overwhelmed treatment plants. Heavy rainfall routinely forced untreated wastewater into the Chicago River system and Lake Michigan. Planning for a permanent solution began in the 1960s, with construction formally launching in 1975 under the oversight of the Metropolitan Water Reclamation District of Greater Chicago. The core of the project consists of more than 100 miles of deep rock tunnels excavated between 150 and 300 feet below ground. These tunnels range from 9 to over 30 feet in diameter and were bored through solid dolomite bedrock using tunnel boring machines customized for long-duration, high-pressure excavation. Construction occurred in phases over several decades, with tunneling largely completed by the early 2000s. The tunnels function as massive underground storage conduits. During storms, combined sewage is diverted from surface sewers into the deep tunnel network, preventing street flooding and uncontrolled discharges into waterways. Once storms pass, the stored water is gradually pumped to treatment plants for processing. This operational strategy required the construction of dozens of drop shafts, some wider than 30 feet, and extending hundreds of feet downward, connecting surface infrastructure to the tunnel system. A second major component of TARP is its reservoir system, which represents the most visible and recent phase of construction. These reservoirs were designed to provide additional storage capacity beyond the tunnels. The largest of these is the Thornton Composite Reservoir, built within a former limestone quarry south of the city. Construction began in the late 1990s, with phased completion allowing partial operation before the full reservoir was finished. When fully complete, Thornton provides over 7 billion gallons of storage, making it one of the largest stormwater reservoirs in the world. Additional reservoirs include the McCook Reservoir in western Cook County. This facility has been constructed in stages, with the first phase becoming operational in the late 2010s. Full completion, including its second major stage, is scheduled for the mid-2020s. Once finished, McCook will add approximately 10 billion gallons of combined stormwater and sewage storage capacity to the system, significantly increasing flood protection for large portions of Chicago and surrounding suburbs. Along a former industrial corridor stretching between Lincoln Park and Bucktown, one of Chicago's most ambitious redevelopment megaprojects has been planned on land that sat underutilized for decades. Lincoln Yards is a proposed large-scale, mixed-use development intended to transform roughly 53 acres along the north branch of the Chicago River into a new urban district, combining residential, commercial, infrastructure, and public space construction. The site historically housed steel mills, manufacturing plants, and later, large-scale storage and light industrial uses. Much of the land required extensive environmental remediation due to contamination from its industrial past. Preparatory work over the past several years has focused on soil cleanup, demolition of remaining industrial structures, and riverbank stabilization, which represent the earliest construction-related activities tied to the project.
The Metro Regional Connector is just 1.9 miles long, but its impact ripples across the entire Los Angeles basin. Beneath the chaotic sprawl of downtown, this subterranean link has silently transformed the backbone of the city's transit network. Not with flashy architecture or sweeping overpasses, but with precision tunneling and deep engineering ambition. It's a megaproject built not to be seen, but to be felt, every time a train glides through the city uninterrupted. Before this connector existed, Los Angeles had a problem. Its growing light rail system, the A, E, and L lines, stopped short of being truly regional. Trains terminated downtown, forcing commuters to transfer between lines, often in disconnected stations, wasting time and discouraging use. The system worked technically, but it didn't flow. It didn't breathe. The regional connector changed that. By boring two parallel tunnels through the dense urban core and tying together these once isolated lines, it created the first true one-seat ride across the county. Now a passenger can board in Azusa and ride directly to Long Beach. East Los Angeles to Santa Monica, no transfers, no transfer platforms, just a straight shot through the city's heart. It's a small piece of track, but a massive leap in connectivity. But connecting three major lines under a century-old city is anything but simple. Downtown LA is layered in complexity, filled with pre-existing tunnels, water mains, sewers, building foundations, earthquake faults, and a living, breathing population above. To carve a clean path through all of it, engineers had to think in three dimensions, navigating not just forward, but over, under, and around everything in their way. The answer came in the form of two tunnel-boring machines, Angeli and Elsie. Each one was a 1,000-ton beast, stretching over 400 feet long, with rotating cutter heads capable of grinding through soil, rock, and buried urban history. But the real trick wasn't speed, it was control. Tunneling through this part of LA meant passing just feet beneath sensitive structures like the historic Broadway corridor and active subway lines, where even the slightest misalignment could cause cracks or settlement. So crews worked slowly, methodically. Pressurized faces on the TBMs stabilized the ground ahead. Real-time monitoring systems tracked every vibration and movement, sending feedback to operators above. In some segments, the margin for error was less than an inch. It was engineering done with surgical precision, buried beneath a city that never stopped moving. At the surface, the work was just as intense. 3 brand new underground stations were constructed: Little Tokyo Arts District, Historic Broadway, and Grand Avenue Arts, Bunker Hill. Each of them had to be excavated in tight quarters, often amid live traffic, aging buildings, and pedestrian zones. The Little Tokyo station posed one of the greatest challenges. Crews had to demolish the existing above-ground station, reroute the tracks underground, and do it all while preserving the cultural heart of a vibrant neighborhood.
At the center of North Texas's expanding regional rail network, the DART Silver Line stands as one of the most complex transportation megaprojects under construction in the Dallas region in 2026. Unlike traditional light rail lines, the Silver Line is being delivered as a commuter-style corridor designed to connect suburban employment centers, major airports, and existing rail systems across multiple cities in Collin, Dallas, and Tarrant counties. The Silver Line is a roughly 26-mile east-west rail corridor stretching from Shiloh Road in Plano to DFW Airport North Station. It repurposes and upgrades an existing freight rail right-of-way, requiring extensive coordination between passenger rail construction and ongoing freight operations. This shared corridor condition defines much of the construction activity occurring in 2026, making the project significantly more complex than greenfield rail lines. By 2026, the Silver Line is firmly in its peak construction phase. Track installation and rehabilitation are ongoing across multiple segments, including full replacement of rail, ties, ballast, and drainage systems to meet passenger rail standards. In several areas, parallel tracks are being added or extended to allow freight and passenger trains to operate simultaneously without service conflicts. These works require nighttime construction windows and precise scheduling to minimize disruption. Station construction is a major focus during 2026. All planned stations serving Plano, Addison, Carrollton, Capel, and DFW Airport are in various stages of vertical construction. Platform structures, canopies, elevators, stairways, and pedestrian bridges are being built concurrently at different sites. In 2026, crews are installing structural steel, pouring elevated platforms, and beginning architectural finishes at stations that reached foundation completion in earlier years. Grade crossing reconstruction defines another major category of 2026 construction. Dozens of roadway crossings along the corridor are being rebuilt or upgraded with new signaling systems, gates, medians, and roadway geometry. Some crossings are being closed or consolidated entirely to improve safety and reduce long-term maintenance. These works require coordination with local municipalities and involve phased traffic shifts that extend throughout the year. Bridge and structure work continues through 2026 at multiple locations. Existing rail bridges are being widened, reinforced, or replaced to support increased rail traffic and modern load requirements. In flood-prone areas, Embankments and culverts are being rebuilt to improve resilience against extreme weather events. These civil works represent some of the most capital-intensive portions of the project. Systems installation accelerates significantly during 2026. Crews are deploying signaling and train control systems designed for higher speed regional rail service. This includes centralized traffic control infrastructure, communication systems, and safety monitoring equipment. Fiber optic networks are being installed along the corridor to support real-time operations, dispatching, and passenger information systems. From a timeline perspective, 2026 is a transition year between heavy civil construction and operational readiness. While earthwork and major structures dominate early phases of the project, 2026 sees a shift towards systems integration, station completion, and corridor-wide testing preparation. Track work and signaling installation continue into 2027, followed by extensive testing and certification. Revenue service is not expected to begin in 2026. Instead, late 2026 and 2027 are dedicated to system testing, operator training, safety certification, and coordination with freight rail partners. Full passenger service is anticipated after completion of these phases, with opening targeted in the latter part of the decade, contingent on testing and regulatory approval timelines. Within the broader context of Dallas megaprojects under construction in 2026, the DART Silver Line is distinct for its regional impact rather than visual prominence. It directly connects major job centers, suburban cities, and DFW Airport without requiring transfers through downtown Dallas. Its construction reshapes an existing rail corridor into a modern passenger system, expanding mobility options across one of the fastest-growing metropolitan regions in the United States.
Brightline West isn't an idea. It's under construction. A $12 billion high-speed rail megaproject designed to link Los Angeles to Las Vegas in just over 2 hours, cutting a trip that often takes over 5 by car. With speeds reaching 200 miles per hour and over 260 miles of new rail corridor, this is one of the largest and most complex infrastructure projects ever attempted in the American Southwest. The alignment runs primarily along the I-15 corridor, chosen for its straight path, existing right-of-way, and the massive volume of traffic it sees. Over 50 million people travel between LA and Las Vegas each year, many of them stuck in stop-and-go congestion. Building next to a major interstate, however, comes with logistical and engineering demands on a different scale. Crews must work within narrow margins between freeway traffic and construction zones, requiring extensive concrete barriers, temporary detours, and phased sequencing to avoid bottlenecks. The trains will operate entirely on dedicated, grade-separated track. That means no level crossings, no signal delays, and no sharing with freight or commuter rail, making Brightline West a true high-speed rail system by global standards. To achieve this, over 300 structures are being constructed along the route, including overpasses, bridges, wildlife crossings, and viaducts. Every one of them is engineered to withstand extreme desert heat, high wind speeds, and seismic loads consistent with California building codes. One of the most technically demanding sections involves crossing the Cayenne Pass, an elevation climb of over 3,000 feet between the Inland Empire and the high desert. This stretch requires extensive cut-and-fill operations, retaining walls and reinforced embankments. Specialized track design, including banked curves and controlled gradients, ensures that trains maintain high speeds without overstressing the vehicles or the infrastructure. Trackbed construction is another layer of complexity. Unlike conventional rail, high-speed systems require exacting tolerances for smoothness and alignment. The subgrade must be compacted and stabilized to millimeter-level accuracy, followed by multiple layers of ballast, reinforced concrete slab track, and vibration-damping materials. These systems are monitored in real time through embedded sensors, allowing for predictive maintenance and immediate response to deviations. Powering the system is an electrified catenary line running the full length of the corridor. This requires constructing hundreds of miles of new transmission infrastructure, including substations, overhead gantries, and high-voltage feeds. To ensure uninterrupted service, the power supply is designed with built-in redundancy and real-time switching capabilities. Utility coordination across 2 states and multiple counties adds further layers of complexity to every mile built. The train sets themselves, based on Siemens Velaro or similar European high-speed rail platforms, will be custom-modified for American standards. Each unit will feature aerodynamic nose cones, regenerative braking systems, crash energy management structures, and lightweight aluminum bodies to reduce axle load and track wear. These aren't commuter trains. They're precision-built machines designed to run at 200 mph across open terrain, with acceleration, deceleration, and safety systems modeled after Japan's Shinkansen and Germany's ICE. Candlestick Point and Hunters Point Shipyard are among the most active megaprojects in San Francisco as of 2026. Spanning more than 700 acres along the city's southeastern shoreline, this redevelopment effort is in full swing, reshaping 2 long-neglected sites into a new urban district. Construction is progressing across multiple parcels, with new streets, housing blocks, and parks taking shape, setting the stage for what will become one of the largest residential and commercial expansions in San Francisco's modern history. At Candlestick Point, where the old stadium was demolished years ago, heavy machinery is grading land for the first wave of residential and retail construction. Multiple mid-rise buildings are rising along a newly gridded street layout. These early phases, expected to complete between 2027 and 2029, will include thousands of homes, many designated as affordable, as well as the backbone of a future retail corridor and public transit connections. Parks and green infrastructure are being built alongside housing, integrating sea level rise protections and climate-resilient landscaping directly into the urban form. To the north, at Hunters Point Shipyard, development is further along. Phase 1 construction is already well underway, with completed townhomes and condos beginning to fill with residents. Additional parcels are actively under construction in 2026, adding new units monthly. Commercial spaces, artist studios, and civic buildings are also under development. Part of the project's goal to restore not just housing, but economic vitality to a part of the city long cut off from opportunity. When fully built out in the early 2030s, the combined Candlestick Hunters Point project will deliver over 12,000 new homes, more than 300 acres of open space, and millions of square feet of office, retail, and cultural uses. It's a complete neighborhood emerging from land that was, for decades, contaminated, fenced off, and largely abandoned. What's distinctive about this project in 2026 is its physical and social scale. This isn't a small infill development or a single commercial tower. It's a city-scale expansion happening within the city limits. Infrastructure is being laid from scratch. Power grids, sewer lines, transit loops, and broadband networks are all part of the foundational work occurring now. Major sections of waterfront are being rebuilt with ecological restoration in mind, with plans for habitat zones, walking trails, and public piers that will eventually reconnect residents with the shoreline. Affordable housing is a central element of the development, and 2026 marks a critical point as the first large wave of affordable units nears completion. These are being reserved in part for legacy residents of Bayview Hunters Point, addressing historic displacement and economic exclusion. Community input remains part of the planning process, particularly in shaping local hiring programs and cultural preservation efforts. Construction challenges remain. Environmental safety is closely monitored due to the site's naval and industrial history. Some parcels require more remediation than others, which is influencing the pace of development. But in terms of raw activity, cranes, crews, and square footage under construction, Candlestick Point and Hunters Point Shipyard rank among the most dynamic megaprojects in San Francisco right now. Where the Port of Los Angeles meets the open Pacific, a vast transformation is underway. Once a place defined by rusted cranes and abandoned warehouses, San Pedro's historic waterfront is being reimagined as a massive public destination. This is West Harbor, a $500 million redevelopment project that's reshaping 42 acres of prime harborfront land into one of the largest and most ambitious waterfront revitalizations in California history. For decades, the San Pedro waterfront was a place of industry. Cargo ships, rail lines, and container yards dominated the landscape, cutting the community off from its own shoreline. The ocean was always there, visible but unreachable. The idea behind West Harbor was radical in its simplicity. Take land that had long been the realm of cranes and commerce and return it to the people. Replace the shipping yards with open promenades. Tear down the fences, open the gates. But turning a gritty, industrial port into a modern, urban waterfront park isn't just a matter of cosmetics. It's an enormous engineering challenge. Beneath the surface, the ground itself needed rebuilding. Years of marine traffic, heavy equipment, and salt exposure had weakened bulkheads and corroded old pilings. Before a single restaurant could open, crews had to stabilize the soil, drive hundreds of deep foundation supports, and upgrade the harbor's edge to withstand both tidal surges and seismic shocks. At the heart of the project is a massive promenade that wraps along the water, designed not just for pedestrians, but for resilience. The concrete pathways are elevated to anticipate sea level rise, with drainage systems engineered to handle storm surges from both land and ocean. New docks are being constructed to support visiting ships and harbor cruises, each one designed with floating gangways that rise and fall with the tides, maintaining access even in extreme conditions. West Harbor isn't just infrastructure, it's experience. The development includes over 150,000 square feet of space for retail, dining, and entertainment, with anchor tenants ranging from artisan markets to major restaurants. A 6,200-seat outdoor amphitheater is being built directly on the waterfront, engineered to deliver concert-quality acoustics in a coastal environment, where sound bounces unpredictably off water and wind. Engineers had to design the stage foundation to accommodate both musical events and the occasional pounding from Pacific storms, using vibration damping, materials, and reinforced steel substructures. All of this, performance spaces, restaurants, shops, sits on land reclaimed from decades of industrial use. That meant a full environmental remediation process, involving soil testing, removal of contaminated fill, and installation of modern stormwater systems to prevent runoff from polluting the bay. A particularly complex element was integrating the new West Harbor seamlessly with the surrounding transportation network. This meant widening roads, building new intersections, and coordinating with nearby freight operations, all while preserving the historic landmarks that give San Pedro its identity. The historic battleship Iowa, docked nearby, had to be factored into every phase of design, ensuring visitor access remained open during construction. The engineering teams also had to work in parallel with the Port of LA's ongoing operations. scheduling pile driving and crane activity to avoid disrupting maritime logistics. Even as the heavy machinery rolls and concrete is poured, the bigger vision is already taking shape. This isn't just about leisure. It's about reconnecting a city with its coastline. For generations, San Pedro's waterfront was a wall of industry. West Harbor turns it into a front porch. Buried beneath the surface of San Francisco's downtown in 2026 is one of the city's most consequential megaprojects under construction, the Portal, also known as the Downtown Rail Extension. This massive underground infrastructure project is finally being realized after decades of delays, aiming to connect Caltrain and eventually California's high-speed rail directly to the Salesforce Transit Center. As of this year, excavation work is ramping up, tunneling contracts are active, and the city is fully committed to completing the extension by the early 2030s. In 2026, the Portal is a hive of subterranean activity. Tunnel boring preparations are in progress, utility relocation is underway, and major downtown streets are experiencing staged disruptions as crews create access points for the underground guideways. It's one of the most complex transportation builds in the Bay Area, requiring coordination beneath some of the densest blocks in the city. Once complete, this megaproject will deliver a seamless rail connection from the peninsula and Central Valley straight into the financial core of San Francisco. The project involves building approximately 1.3 miles of new track, mostly underground, to link the existing Caltrain line near 4th and King with the Salesforce Transit Center. In 2026, the staging areas at both ends of the project are fully operational. Pile driving, shoring walls, and structural reinforcements are all happening in real time as the city begins to carve out the physical corridor that will carry thousands of passengers daily. Construction in and around Townsend, 2nd Street, and the south of Market area is active and accelerating, with visible impacts above ground and substantial progress being made below it. The Portal isn't just a rail project, it's a regional unlock. In 2026, Caltrain still terminates at 4th and King, about a mile short of downtown. That last mile has long been the missing link in Bay Area transit. By closing that gap, this project will plug regional rail directly into San Francisco's business core, reducing car dependency and reshaping how people move across the region. When complete, the Portal will allow Caltrain riders to disembark in the heart of the city and will set the stage for future high-speed rail service to run directly from Los Angeles to downtown San Francisco, without transfers. The current timeline targets a completion date in the early 2030s, with most heavy construction expected to occur between 2026 and 2030. In the context of San Francisco's other megaprojects under construction right now, the Portal stands out for its invisibility. Most of the work is happening underground, but the scale of its impact will rival that of any tower or waterfront redevelopment. Cost is high, risk is real, and coordination is intense. Crews are navigating under live utilities, major foundations, and transit lines. Every foot of tunnel requires precision, and every stage of construction must account for seismic resilience, waterproofing, and integration with existing BART and MUNI infrastructure. In 2026, engineering teams are deep into geotechnical work and soil stabilization, preparing for the eventual tunnel boring operations that will begin in earnest in 2027. In 2026, one of San Francisco's most strategically important megaprojects under construction is taking shape across the Caltrain rail yards in the heart of central SOMA. This isn't just a housing or transit upgrade. It's a massive reimagining of over 20 acres of publicly owned rail-adjacent land that has long divided the neighborhood. As construction pushes ahead this year, The rail yard redevelopment is steadily moving from planning to reality, with early phases under active build-out and long-term infrastructure elements aligning with the city's broader transit goals. Right now, in 2026, the site is in the thick of foundational construction. Crews are laying the groundwork, literally, for what will eventually be a dense, mixed-use district layered above and around the working Caltrain tracks. This megaproject is part of a coordinated effort to modernize regional transportation while unlocking thousands of new homes and millions of square feet of development potential just blocks from downtown San Francisco. The Caltrain yard has been a physical and visual barrier in central SOMA for generations. But in 2026, construction is actively transforming this space into an urban connector. Elevated platforms, decked structures, and street-level improvements are all in progress, designed to bridge the gap between surrounding neighborhoods and the core rail infrastructure. This year, much of the work focuses on realigning utilities, stabilizing the site for future vertical construction, and preparing parcels that will be used for new housing, office towers, and public spaces. The housing element of the rail yard redevelopment is one of the most anticipated components currently under construction. Phase 1 will deliver several hundred new residential units, with a significant portion allocated for affordable housing. These buildings, now rising on the edges of the yard, are expected to be ready for occupancy by 2028. Eventually, the full build-out will add thousands of homes to one of the city's most transit-rich locations, housing that is critically needed as San Francisco continues to face supply pressures. But housing is only one piece of this megaproject. In 2026, work is also underway on commercial development that will bring job space to the corridor, particularly targeting sectors like life sciences, tech, and creative industries. The close proximity to both downtown and future rail connections makes this site highly desirable, and the ongoing construction reflects the urgency to activate it. Several mid-rise office buildings are being framed out this year, with completion of the first wave of commercial space projected around 2029. A crucial component that's being integrated into the redevelopment in real time is transportation. The Caltrain facility itself is being reconfigured to prepare for electrification, high-speed rail integration, and potential undergrounding as part of the downtown rail extension. In 2026, while major tunneling has not yet reached the yard, planning and structural coordination are fully underway to make sure future rail service, including high-speed trains, can be accommodated. This makes the rail yard site not just a place to live and work, but a critical node in the future of statewide transit.
Occupying the geographic and economic heart of Miami's financial district, Brickell City Center stands as one of the largest and most technically ambitious urban megaprojects ever constructed in South Florida. Brickell City Center is a multi-phase, mixed-use development spanning roughly 4 city blocks in the Brickell neighborhood. The project was conceived to redefine high-density urban construction in Miami by combining retail, office, residential, hospitality, and transit infrastructure within a single integrated footprint. Planning began in the late 2000s, with the formal development advancing in the early 2010s as Brickell rapidly transitioned from a low-rise banking district into a vertical urban core. Construction officially began around 2012, starting with extensive site preparation and demolition of existing structures. The scale of the project required a complete reconfiguration of underground utilities, including new water, sewer, electrical, and telecommunication systems capable of supporting millions of square feet of development. Deep excavation followed, with dewatering systems installed to manage Miami's high groundwater levels during foundation work. At the structural level, Brickell City Center required a complex system of reinforced concrete cores, transfer slabs, and podium structures. The development includes multiple residential towers, 2 major office towers, a hotel tower, and a large retail and entertainment podium. Each tower was built using high-strength concrete and deep pile foundations drilled into limestone bedrock to handle vertical loads and wind forces. One of the defining construction features of Brickell City Centre is the climate ribbon, an elevated architectural canopy spanning the retail core. This structure required long-span steel framing and custom fabricated components designed to provide shade, ventilation, and rain protection in a subtropical climate. Installation of the climate ribbon occurred during the later stages of podium construction and required precise sequencing above active work zones. The retail podium itself was constructed as a multi-level structure occupying the center of the site. Large column-free interior spaces were achieved through the use of transfer beams and post-tension slabs. Mechanical and electrical systems were embedded within the podium to serve both retail tenants and the towers above, reducing redundancy and optimizing space. Office construction included 2 Class A towers designed to modern seismic, wind, and hurricane standards. These towers required curtain wall systems engineered for high wind resistance and solar control. Interior build-outs were completed after core and shell construction, with phased tenant occupancy beginning shortly after structural completion. Residential construction was delivered across several towers, each with distinct layouts but shared infrastructure systems. Vertical construction of these towers progressed concurrently, requiring careful coordination of cranes, concrete pours, and material logistics within a confined urban site. Residential units began delivering in phases starting in the mid-2010s. Hospitality construction included a high-rise hotel tower integrated into the overall podium. This required specialized structural and mechanical design, including back-of-house service zones, conference facilities, and rooftop amenities. Hotel construction was completed alongside residential phases to align with the overall project schedule. Transit integration was a major component of Brickell City Centre's construction scope. The project directly connects to the Metro Mover system, requiring new station interfaces, elevated walkways, and structural modifications to existing transit infrastructure. These connections were built while the Metro Mover remained operational, adding complexity to sequencing and safety planning. The construction timeline unfolded in defined phases. Major vertical construction occurred between approximately 2013 and 2015. The retail component of Brickell City Centre opened in late 2016, marking a key milestone for the project. Office and residential towers reached substantial completion around the same period, with additional residential deliveries extending into 2017. From a mega-project perspective, Brickell City Centre was notable for its centralized construction management and financing structure, allowing multiple buildings to rise simultaneously rather than sequentially. This approach shortened the overall development timeline, but increased coordination demands across trades and contractors. Set within the dense fabric of downtown Miami, MiamiCentral represents one of the most complex privately delivered mega projects ever completed in the city, combining rail infrastructure, vertical construction, and urban redevelopment into a single coordinated build. MiamiCentral is a mixed-use, transit-oriented development centered on the southern terminus of Brightline's intercity rail system. The project occupies multiple city blocks between Northwest 1st Avenue and Northwest 6th Street, directly adjacent to Government Center. Planning for MiamiCentral began in the early 2010s as part of a broader effort to reintroduce intercity passenger rail to Florida, while simultaneously redeveloping underutilized downtown land. Construction officially began around 2014, with early work focused on site preparation, demolition of existing low-rise structures, utility relocation, and rail corridor reconstruction. The project required rebuilding active rail alignments, while maintaining freight operations on the Florida East Coast Railway, necessitating phased construction sequencing and temporary track realignments. At the core of MiamiCentral is the Brightline station, constructed as an elevated rail terminal spanning multiple blocks. The station structure required long-span concrete and steel framing to support train platforms above street level while allowing uninterrupted traffic flow beneath. Platform construction included high-load track slabs, vibration mitigation systems, signaling infrastructure, and integrated safety systems compliant with federal rail standards. Below and around the station, the project incorporated significant structural podium construction. Large transfer slabs were built to distribute loads from residential towers above while accommodating open concourses, retail space, and passenger circulation areas below. This approach allowed rail, pedestrian, and vehicular systems to coexist within a constrained urban footprint. MiamiCentral includes multiple high-rise towers developed in phases. The first residential towers began vertical construction after the station structure was well underway. These towers required deep foundations and auger-cast piles to manage Miami's soil conditions and groundwater levels. Structural systems used reinforced concrete cores with flat plate floor construction, optimized for residential occupancy and high-rise efficiency. In addition to residential units, MiamiCentral incorporated office space, hotel components, and retail frontage. Mechanical, electrical, and plumbing systems were designed to operate independently across uses while sharing centralized infrastructure where possible. Loading docks, service corridors, and back-of-house systems were embedded into the lower levels to minimize surface disruption. A defining construction challenge was integrating multiple transportation modes into a single site. MiamiCentral connects Brightline Intercity Rail, Metro Rail, Metro Mover, Metrobus, and pedestrian networks. Construction included new elevated walkways, platform connections, fare control zones, and vertical circulation systems, linking existing transit infrastructure to newly built spaces. Roadway reconstruction was another major component. Portions of Northwest 1st Avenue and surrounding streets were rebuilt to accommodate new traffic patterns, curbside loading, and pedestrian access. Streetscape improvements included drainage upgrades, structural decking over rail corridors, and reinforced pavement designed for heavy service vehicles. The timeline of MiamiCentral unfolded in stages. Rail corridor and station construction progressed between roughly 2014 and 2017. The Brightline station reached functional completion in late 2017, coinciding with the launch of passenger service between Miami and Fort Lauderdale, later extended to West Palm Beach. Full station operations began in early 2018. Residential towers were delivered in phases, with initial buildings completed around 2018 and additional towers finishing in subsequent years. Retail and public spaces opened gradually as tenant build-outs were completed. The project did not conclude with a single completion date, but by the late 2010s, MiamiCentral was fully operational as a transit hub and mixed-use district. Within the context of Miami's biggest megaprojects, MiamiCentral stands out for being privately financed and rail-centric. Unlike publicly led infrastructure efforts such as the Port of Miami Tunnel or airport expansions, MiamiCentral combined transportation infrastructure with real estate development under a single master plan. This approach shifted how large-scale projects could be delivered in Miami's urban core. From a construction management perspective, MiamiCentral required coordination among rail engineers, vertical construction contractors, transit agencies, and city departments. Work occurred simultaneously above, below, and alongside active transit lines, requiring constant monitoring of settlement, vibration, and structural movement. By the middle of the decade, one of North Texas's earliest soccer-specific stadiums is undergoing a comprehensive reconstruction that places it firmly among Dallas area megaprojects active in 2026. The new Toyota Stadium redevelopment in Frisco represents a multi-year modernization effort focused on structural capacity, revenue generation, climate mitigation, and long-term event flexibility rather than a simple renovation. Toyota Stadium originally opened in 2005, designed for a different era of Major League Soccer and a much smaller regional population. The redevelopment project restructures the existing stadium rather than replacing it, allowing FC Dallas to continue operations while construction advances in carefully sequenced phases. By 2026, the project is deep into its most technically demanding stage, with heavy construction occurring throughout the seating bowl, concourses, and building systems. Construction work during 2026 concentrates on major structural modifications. Entire sections of the lower bowl are being demolished and rebuilt to adjust rake angles, improve sightlines, and support additional vertical loads from new premium levels above. New concrete pours and steel framing are installed in phases to maintain stadium stability, while adjacent areas remain operational. This year also includes reinforcement of existing foundations to meet updated building codes and support heavier roof and canopy systems. One of the most visible construction efforts in 2026 is the installation of expanded canopy structures. These roof elements are designed to significantly increase shaded seating, addressing long-standing heat exposure issues. The canopy construction involves large-span steel trusses, integrated lighting mounts, and future-ready broadcast attachment points. Installation is staged section by section to allow partial stadium use during the soccer season. Premium seating and hospitality spaces dominate interior construction in 2026. New club lounges, lodge boxes, and suites are being built into previously underutilized stadium volume. This requires extensive mechanical and electrical upgrades, including new air handling units, upgraded power distribution rooms, and expanded data infrastructure. Plumbing systems are also being replaced or rerouted to serve higher capacity food and beverage operations. Concourse reconstruction is another major focus in 2026. Existing concourses are being widened, regraded, and reconfigured to improve circulation and accessibility. Vertical transportation systems, including elevators and stairs, are being added or relocated to comply with modern accessibility standards. These changes require careful coordination between demolition crews, concrete teams, and utility installers to avoid service disruptions. Technology infrastructure work accelerates during 2026. Crews are installing new fiber optic backbones, wireless access systems, and security networks throughout the stadium. Dedicated broadcast rooms and control spaces are under construction to support national and international television requirements. These systems are designed to accommodate future tournaments and non-soccer events without additional major retrofits. Outside the stadium bowl, 2026 construction includes the redevelopment of surrounding plazas and entry zones. Pedestrian circulation is being improved through expanded hardscape areas, upgraded lighting, and reworked security screening layouts. These exterior improvements are engineered to support higher peak attendance and year-round events, not just match days. Sustainability measures are integrated into the 2026 construction scope. Lighting systems are being converted to high-efficiency LED fixtures. Water infrastructure is upgraded with low-flow systems, and stormwater management improvements are installed to reduce runoff during heavy rain events. Older materials removed during demolition are being recycled or reused where feasible to reduce construction waste. From a timeline perspective, 2026 represents the midpoint of the redevelopment. Structural and exterior envelope work dominates early and mid-year, while interior build-outs continue into late 2026 and beyond. Some premium areas and upgraded seating sections are expected to open in phases as construction completes, allowing incremental increases in stadium functionality. Major construction activity is scheduled to continue through 2027, with final interior finishes, technology commissioning, and operational testing extending into late 2027. Full project completion is expected between late 2027 and 2028, depending on seasonal construction constraints and event scheduling. The phased delivery approach ensures continuous stadium use while transitioning the facility to its final configuration. Covering more than 27 acres across multiple downtown blocks, Miami Worldcenter is not a single construction project, but a layered mega project built through coordinated phases that collectively reshaped the northern edge of downtown Miami. Miami Worldcenter is located north of the Central Business District, bounded generally by Northeast 2nd Avenue, Interstate 395, and Northeast 8th Street. The site consisted for decades of underutilized parcels, surface parking, and fragmented low-rise structures. Formal planning for redevelopment began in the early 2000s, with land assembly occurring gradually over many years. The scale of the site required a master-planned approach rather than a single build execution. Major construction activity began in the mid-2010s, following zoning approvals and infrastructure agreements with the City of Miami and Miami-Dade County. Early phases focused on horizontal construction, including demolition, mass grading, utility relocation, and the installation of new underground infrastructure. Water, sewer, power, communications, and stormwater systems were rebuilt to support millions of square feet of future development. A defining construction element of Miami Worldcenter was its internal street grid. New public streets were carved through the site, requiring roadway construction, drainage systems, sidewalks, lighting, and streetscape elements. These streets were designed to function as permanent city infrastructure rather than private access roads, integrating the development into the surrounding urban fabric. Vertical construction followed in multiple, overlapping phases. Residential towers were among the first major structures to rise, each requiring deep foundations suited to Miami's limestone geology and high groundwater conditions. Pile foundations, reinforced concrete cores, and high-rise flat-plate floor systems were used across most towers, with construction sequenced to allow simultaneous builds on adjacent parcels. Retail and commercial structures were developed at the podium and street levels. These buildings required large-span structural systems to create flexible interior layouts for tenants. Mechanical and electrical systems were distributed through shared service corridors to reduce redundancy across the district. Loading docks and service access points were consolidated to minimize street-level disruption. One of the most significant infrastructure integrations within Miami Worldcenter was its relationship with regional transit. The development was designed around proximity to Brightline's MiamiCentral station, as well as Metro Rail, Metro Mover, and bus connections. Pedestrian corridors and public spaces were constructed to funnel foot traffic between transit nodes and interior blocks, requiring careful grading and structural decking over below-grade utilities. Construction timelines varied by parcel. Early residential and retail components began delivering units around 2018 and 2019. Additional towers and commercial buildings were completed in the early 2020s, with construction continuing in phases as market conditions and financing allowed. Unlike a single mega project with a fixed end date, Miami Worldcenter evolved through staggered completions. Hotel construction formed another major component. Large hospitality structures required distinct structural and mechanical systems, including back-of-house service cores, conference, spaces, and rooftop amenities. These buildings were constructed concurrently with residential towers, increasing logistical complexity across the site. Parking infrastructure was largely integrated into podiums and below-grade levels. This required excavation, dewatering, and reinforced slab construction beneath active building sites. Parking systems were designed to serve multiple uses, including residential, retail, and event traffic, reducing the need for standalone garages. From a construction management perspective, Miami Worldcenter required coordination across dozens of contractors, architects, and engineers. Crane operations, concrete pours, and material deliveries were scheduled to avoid conflicts within a dense, active site. Safety planning was critical due to the proximity of Interstate 395 and ongoing city traffic. The megaproject also included public space construction, such as plazas and pedestrian promenades. These areas required structural support for landscaping, irrigation systems, and integrated lighting. Public realm construction often occurred late in each phase, following heavy structural work.
Some airports evolve slowly, layer by layer, molded by decades of growth. George Bush Intercontinental Airport in Houston, however, was born with a blueprint for scale from the very beginning. Constructed in the late 1960s to relieve pressure on the aging William P. Hobby Airport, IAH was never intended to be a simple regional terminal. It was a forward-looking investment, a modern answer to the booming oil economy and Houston's ascent as a global city. The site selected was expansive, a heavily forested stretch of North Houston that offered the space needed to dream big. Clearing the land was a massive undertaking on its own, requiring the removal of dense vegetation, rerouting of creeks and water flows, and the construction of entirely new utility corridors before the first runway could even be considered. Once the land was prepped, construction began with an ambitious but calculated layout. Instead of a single terminal, the airport would use a decentralized, multi-terminal model, with each terminal functioning semi-independently while connected via road and eventually underground train. This modular design was intended to accommodate rapid expansion without crippling the core infrastructure. Each terminal could grow, be retrofitted, or replaced without overhauling the entire system. Early construction focused on 3 primary terminals, A, B, and C, each rising in parallel over poured concrete foundations and skeletal steel frameworks. The terminal buildings themselves were constructed with long-span trusses, allowing for wide, open concourses that minimized interior columns and maximized flexibility for airline operations. As the airport expanded, so too did its runways, crafted to handle the full spectrum of aircraft, including wide-body international jets and high-volume domestic carriers. Runway construction required extensive excavation and grading work to create a perfectly level base in Houston's famously unstable clay-heavy soil. Crews implemented multi-layered sub-base systems, including geotextile membranes, to prevent cracking and heaving from the area's intense rainfall and temperature swings. Parallel runways were spaced widely enough to allow simultaneous takeoffs and landings, an operational advantage critical to IAH's future role as a hub. Throughout the 1980s and 1990s, construction never truly stopped. Terminal C was expanded into a major domestic hub for Continental Airlines, and later, Terminal E was constructed as an international gateway. The development of Terminal E marked a shift toward high-capacity, high-efficiency construction. It featured dual-level road access, streamlined customs and immigration facilities, and modern jet bridges designed for next-generation aircraft. The supporting infrastructure was just as critical. New parking structures, maintenance facilities, and de-icing pads were all built to support the increasing traffic load. Simultaneously, the airfield lighting, navigational aids, and fueling systems underwent modernization to comply with FAA regulations and future-proof the site. Beneath the terminals, the construction of the airport's people mover system added a layer of subterranean complexity. Engineers bored deep into Houston's wet subsoil to install guideways and tunnels for the train, requiring continuous dewatering, careful slope stabilization, and waterproofing membranes to prevent long-term seepage and erosion. The result was a fully automated train system that allowed passengers to move between terminals without surface traffic interference, an operational necessity in an airport spread across thousands of acres. Every phase of expansion at IOH has demanded not just engineering expertise, but logistical acumen. The airport had to remain operational throughout each construction phase, meaning crews often worked overnight or in carefully isolated zones to avoid disrupting flight schedules. Coordinating contractors, security, utilities, and aviation authorities required a master-level orchestration of timelines and contingency planning. Yet through each stage, whether laying runway concrete under humid Gulf skies or welding steel at height, Houston's flagship airport grew into a true international gateway, one poured and riveted together by sheer logistical ambition. It began not with a single building or base, but with the largest American military construction project undertaken overseas since the end of World War II. Camp Humphreys, located in Pyeongtaek, South Korea, evolved from a modest airfield into the sprawling nerve center of U.S. military power in Northeast Asia, a transformation that required nearly 2 decades of relentless engineering, logistics, and international coordination. The expansion was initiated in the early 2000s as part of a strategic realignment between the United States and South Korea. The goal was to relocate the majority of U.S. forces from their vulnerable position in Seoul, just 40 miles from the DMZ, to a more defensible location farther south. Camp Humphreys, already housing a small contingent of U.S. personnel, was selected as the anchor site for this megaproject. The scope of construction was immense. Over 3,500 acres of land had to be secured, making it the largest U.S. military installation in the world by size. This required the relocation of several nearby South Korean villages, the rerouting of major roads, and a complex land reclamation process to prepare the site for development. The total area more than quadrupled, turning the base into a small city engineered for permanent, high-capacity occupation. More than 650 buildings were constructed, including headquarters for U.S. Forces Korea, family housing towers, barracks, schools, hospitals, logistics hubs, and training facilities. The site was master planned with the expectation of housing over 35,000 people, including soldiers, civilians, and their families. Infrastructure included not just military assets, but complete civilian support systems, utility grids, water treatment plants, retail centers, and even fire stations. To ensure uninterrupted operations under wartime conditions, the base was built with hardened command bunkers, redundant power supplies, and secure communication systems linked to the wider U.S. Indo-Pacific Command Network. Military logistics facilities included armored vehicle motor pools, aerial drone hangars, ammunition depots, and helicopter landing zones, all constructed to withstand both conventional and asymmetric attacks. One of the project's biggest engineering challenges was building on previously undeveloped and flood-prone land. Massive drainage systems were installed, along with deep foundations for major structures. Environmental impact mitigation required advanced soil stabilization and water diversion techniques to accommodate the region's heavy seasonal rains. Construction was overseen jointly by the U.S. Army Corps of Engineers and South Korea's Ministry of National Defense. At its peak, more than 17,000 workers were involved in daily operations, using heavy equipment and modular assembly techniques to accelerate progress. Prefabricated components were shipped in bulk from both domestic and international suppliers to meet deadlines and cost targets. The base is structured with a dual-purpose design philosophy: readiness and endurance. Warfighting infrastructure is integrated seamlessly with daily life systems. The command centers are located beneath reinforced buildings, while key logistical routes are protected by anti-vehicle barriers and surveillance perimeters. Internal road networks, emergency evacuation paths, and refueling points are all planned with conflict scenarios in mind. Strategically, Camp Humphreys is more than a relocation. It represents a long-term geopolitical bet. The base gives the United States deep operational reach into the Korean Peninsula, China, and the broader Indo-Pacific region. It acts as a launch point for rapid deployment, intelligence coordination, and allied joint operations, all while sitting well beyond immediate North Korean artillery range. The megaproject was funded largely by South Korea, covering roughly 90% of the multi-billion-dollar cost as part of the country's defense cost-sharing agreements. This level of investment underscores the strategic importance both nations place on the site, not just as a military base, but as a symbol of enduring alliance.
Anchored along the banks of the St. Johns River in downtown Jacksonville, the development of Riverfront Plaza required a deliberate fusion of civil engineering, landscape architecture, and waterfront resiliency planning. The site, once occupied by the old Jacksonville Landing Marketplace, was reimagined as a dynamic public space integrating structural components with flood mitigation strategies, all while maintaining connectivity to adjacent urban infrastructure. From a construction and engineering standpoint, this project represented a complex interplay between environmental restoration, soil stabilization, urban utility integration, and open space programming. The first stage of construction focused on complete site clearing and demolition of the former structures. This phase involved selective dismantling techniques to minimize dust and vibrations, as the site is located near active traffic corridors, office buildings, and riverwalk segments. Demolition debris was sorted and recycled as part of a broader sustainability mandate, and existing below-grade utilities were mapped, capped, or rerouted to prepare the site for redevelopment. With demolition complete, the site was surveyed in high resolution to inform the grading and drainage plans. Given its proximity to the river and its susceptibility to tidal fluctuations and storm surges, the grading plan called for subtle terracing and the integration of bioswales to manage stormwater naturally. Fill material was imported and compacted in lifts, each tested for density and moisture content to prevent future settlement. Geotextile membranes were installed between fill layers to enhance soil stability and prevent erosion along the river's edge. One of the central challenges of the Riverfront Plaza redevelopment was the construction of structural retaining elements and hardscape features capable of withstanding both pedestrian use and hydrodynamic forces. Reinforced concrete retaining walls were formed along the Riverwalk edge, designed with weep holes and subdrain systems to relieve hydrostatic pressure. These walls were anchored into the subgrade with helical piles in areas with softer soils, ensuring long-term stability against the variable forces of tidal surge and river currents. The plaza itself was constructed using a combination of cast-in-place and precast concrete paving systems, arranged in geometric patterns and supported by a subbase of compacted aggregate and fine leveling sand. Embedded conduits and utility chasers were integrated beneath the hardscape to support lighting, irrigation, and security systems. Special attention was given to expansion joints and surface drainage in the plaza design, with trench drains and permeable surfaces used to quickly shed water and avoid pooling during heavy rains. To support programming flexibility, the site included several utility stub-outs and foundational footings for potential future vertical structures such as pavilions or public art installations. Electrical cabinets and water connections were recessed and weatherproofed, and fiber optic conduits were installed for surveillance and wireless communication infrastructure. Landscape elements, including native trees, shrubs, and grasses, were selected for salt tolerance and deep root structures to minimize wind throw during storms. Tree pits were designed with structural soils and root barriers to protect adjacent pavement. Lighting was provided through architectural-grade LED fixtures mounted on concrete bases or embedded in pathways for both aesthetic and functional illumination.
Rising from Estonia's pine-covered plains near Tapa, Camp Rito represents one of NATO's most forward-deployed military megaprojects, engineered to support rapid reaction forces at the doorstep of Russia. This base was not built as a symbol, but as a highly functional logistics and combat hub, constructed to sustain prolonged operations in a high-threat environment. The strategic logic behind Camp Rito is clear. Estonia shares a direct land border with Russia. In the wake of renewed geopolitical tension in Eastern Europe, NATO required a hardened, rapidly deployable footprint on the eastern flank. Camp Rito was designed to host rotating multinational battle groups under NATO's Enhanced Forward Presence framework, enabling a permanent Allied presence without formal basing agreements. Construction began in the mid-2010s as part of a multi-phase infrastructure expansion program. The site was selected for its proximity to both rail and road arteries, as well as its access to the nearby Tapa military training area. Estonia's largest, allowing for live fire exercises and armored maneuver drills within minutes of the base perimeter. Engineers laid out the facility with modular expansion in mind. Pre-stressed concrete foundations were poured for over 100 buildings, including barracks, armored vehicle shelters, logistics warehouses, dining halls, ammunition storage bunkers, and maintenance depots. Many of these structures were prefabricated in segments to accelerate construction timelines and reduce supply chain dependency. Vehicle infrastructure was prioritized. Camp Rito includes reinforced roads capable of supporting tanks, IFVs, and heavy artillery under all weather conditions. De-icing systems were installed on key pathways to ensure mobility through Estonia's harsh winters. Fuel depots were built with dual-hardened containment systems, allowing the refueling of armored units on-site without external support. The camp's power grid includes redundant diesel generators and battery arrays. Electrical wiring was embedded with EMP-resistant shielding, and communications were integrated into NATO's secure digital backbone. Satellite uplinks, encrypted fiber lines, and field-hardened server rooms were added to ensure uninterrupted command and control capabilities. Each barracks block is fitted with internal NBC filtration systems. Heating systems are fully winterized, with underground insulation around all water and sewage systems to prevent freezing. Tactical operations centers are located in reinforced concrete bunkers partially submerged for added blast protection. Water security was a key challenge. Engineers drilled deep bore wells and installed purification systems with triple redundancy, ensuring a clean water supply even during siege or isolation scenarios. Wastewater is processed on-site in a closed-loop treatment facility, compliant with NATO environmental standards. The base also includes a secure arms depot with access-controlled vaults, shock-proof internal walls, and fire suppression systems that operate independently from the base grid. Ammunition storage was built with blast relief tunnels, angled shafts designed to vent any accidental detonation away from personnel quarters. Camp Rito's design includes pre-surveyed landing zones for NATO helicopters and temporary pads for vertical lift drones. The outer perimeter is protected by layered defenses, anti-vehicle trenches, motion detection fencing, infrared surveillance, and pre-positioned rapid response points for mounted patrols. While multinational forces rotate through on a regular basis, primarily British, French, and Danish units, the camp is operated in close partnership with the Estonian Defence Forces. Every system, from vehicle compatibility to radio frequencies, was built for interoperability with Allied forces from the outset. At the height of the Cold War, while the world stood on edge beneath the specter of nuclear annihilation, the United States embarked on one of its most ambitious military engineering projects, hollowing out the core of a granite mountain to build a fortress that could survive the end of the world. This became the Cheyenne Mountain Complex, a hardened command and control installation designed to absorb the unimaginable and keep operating. Excavation began in 1961 in Colorado Springs, Colorado, on the eastern slope of the Rocky Mountains. Engineers drilled and blasted through nearly 700,000 tons of solid granite to carve out a vast internal network of chambers, tunnels, and infrastructure. The granite was selected not for beauty, but for density and stability. Its shock-absorbing properties were critical in the event of a nearby nuclear blast. Inside, 15 independent buildings were constructed, each mounted on over 1,300 steel springs, capable of swaying independently to absorb seismic shock. These buildings were not simply placed on bedrock. They were suspended within the mountain's hollowed core like floating islands of steel and concrete, isolated from the earth to maximize survivability. Each spring was rated to deflect up to 18 inches in any direction. The complex was designed to withstand a 30-megaton blast as close as 2 kilometers away. Blast doors weighing 25 tons sealed the entrances, and every major system inside had multiple redundancies. Air intakes were filtered through massive banks of scrubbers to remove radioactive, chemical, or biological contaminants. The water system drew from an underground reservoir, and backup diesel generators could keep the facility running independently for months. The construction took 6 years and involved thousands of workers, operating under extreme security and secrecy. Much of the interior concrete was poured under tightly controlled conditions to meet military specifications for strength and radiation shielding. Electrical systems were buried and shielded to resist electromagnetic pulses, and communication lines were hardened to maintain contact with key command centers like the Pentagon and NORAD's other facilities. By 1966, the Cheyenne Mountain Complex was fully operational. Its primary mission was to serve as the command center for NORAD, the North American Aerospace Defense Command, tasked with monitoring and responding to any missile threats against North America. Radar feeds, satellite data, and early warning systems all converged here, where military analysts tracked potential nuclear launches in real time and coordinated defensive responses. The layout of the complex includes over 4.5 acres of internal floor space. More than a mile of tunnels connects operation centers, data rooms, dormitories, dining facilities, and even a medical bay. Every piece of equipment was selected for durability under catastrophic conditions, and everything from door frames to wiring was built with the expectation that it might one day be tested in the most extreme scenario imaginable.
North of Dallas, in one of the fastest-growing urban corridors in Texas, the Fields Entertainment District in Frisco is emerging as a large-scale, mixed-use mega project that is actively under construction in 2026. The development is positioned within the broader Fields master-planned community, a multi-thousand-acre site designed to accommodate long-term population growth, corporate expansion, and regional tourism demand. The Fields Entertainment District is planned as a dense concentration of sports, hospitality, retail, dining, and public space, anchored by major destination users rather than traditional suburban commercial formats. Unlike single-purpose developments, the district is structured to operate continuously, supporting large events, daily foot traffic, and future transit-oriented growth. Its scale and phasing place it among the most consequential Dallas area megaprojects progressing through construction in 2026. By 2026, horizontal infrastructure work is largely complete, allowing vertical construction to dominate activity across the district. Roadways, utility corridors, stormwater systems, and site grading were established in earlier phases, enabling simultaneous construction of multiple buildings. In 2026, cranes, concrete crews, and steel framing operations are active across entertainment venues, hotels, parking structures, and retail blocks. One of the primary construction focuses in 2026 is vertical development of large format entertainment and event buildings. These structures require long-span steel framing, high-capacity foundations, and extensive back-of-house infrastructure. Construction includes structural steel erection, roof decking, and exterior enclosure systems designed to accommodate high occupant loads and advanced audiovisual systems. These buildings are engineered to support concerts, live events, and large public gatherings. Hospitality construction accelerates during 2026. Multiple hotel components within the district are rising simultaneously, with reinforced concrete and steel structures progressing floor by floor. Interior build-outs begin on lower levels as upper floors continue structural work. Mechanical and plumbing systems are sized for high turnover and large conference or event-driven occupancy patterns, reflecting the district's destination-oriented role. Retail and dining blocks are also under active construction in 2026. These buildings are designed with flexible floor plates to allow tenant customization while maintaining consistent architectural standards across the district. Construction includes storefront framing, exterior finishes, service corridors, and shared utility infrastructure. Emphasis is placed on pedestrian connectivity with covered walkways, plazas, and integrated outdoor seating areas built alongside vertical elements. Parking infrastructure represents a significant portion of 2026 construction activity. Multi-level parking garages are being built to serve entertainment venues, hotels, and retail uses. These structures require rapid cycle concrete construction and are designed with future adaptability in mind, allowing potential conversion or integration with autonomous or shared mobility systems later in the project's life cycle. Public realm construction expands significantly in 2026. Central gathering spaces, landscape plazas, and pedestrian spines are being formed as adjacent buildings reach enclosure stages. Hardscape installation, lighting systems, wayfinding infrastructure, and drainage features are constructed concurrently to ensure these spaces are operational as individual components of the district open. These areas are engineered to manage large crowd movements during peak events. Utility and systems integration is a major technical focus in 2026. Electrical substations, district-wide communications networks, and centralized security systems are being installed to support high-demand uses. Fiber networks are integrated throughout the district to support digital signage, ticketing systems, and event broadcasting. These systems are coordinated across multiple buildings to function as a unified operational environment. Well before the first match of the 2026 FIFA World Cup is played in North Texas, downtown Dallas is undergoing a coordinated series of infrastructure and venue upgrades that collectively form one of the region's most complex mega-project efforts active during 2026. Rather than a single construction site, the World Cup preparations consist of multiple overlapping projects focused on transportation, public space, security, mobility, and event operations, many of which reach peak construction or final delivery during 2026.
They didn't just build an airport on the shores of the Black Sea. They carved a new future for a nation out of rock, sea, and ambition. The construction of Istanbul Airport, one of the most audacious infrastructure projects of the 21st century, was not just a matter of civil engineering. It was a national statement, a vision chiseled into existence with relentless speed and almost cinematic scale. From the very first shovel of Earth, this project wasn't designed to follow global aviation standards. It was meant to redefine them. The site itself was a challenge from the start. A mix of former open-pit coal mines, wetlands, and unstable terrain that required millions of cubic meters of earth to be moved, compacted, and stabilized. This wasn't just land reclamation, it was land transformation on a continental scale. Thousands of workers labored around the clock, building not only runways and terminals, but the very ground those structures would stand on. The scale of the terminal alone is staggering. Designed to be the largest under a single roof anywhere on Earth, the main passenger terminal covers over 1 million square meters. Its skeleton is steel, its skin glass and aluminum, but its foundation is poured from unflinching confidence. Every beam, every column was part of a choreography measured in millimeters, but executed at megastructure scale. Construction teams sourced materials from all over Turkey and beyond, fueling a logistical operation that mirrored military precision. Concrete was poured by the ton, and cranes moved like clock hands over the site, some of them among the tallest and most powerful in the world. And at the heart of it all, the project had to maintain momentum in a political and economic climate that was, at times, deeply volatile. Timing was everything. The goal was clear from the start. Open fast, open big. Unlike projects that slowly build up capacity, Istanbul Airport was envisioned to make a splash from day one. That meant building not one, but multiple parallel runways right from the outset, designed to handle hundreds of flights a day with minimal delay. The air traffic control tower, with its sleek tulip-inspired silhouette, was one of the first structures to rise, signaling the pace and design sophistication the rest of the site would follow. Around it, a spiderweb of service roads, utility tunnels, fuel lines, and drainage systems had to be laid out with unerring accuracy. Every inch of the infrastructure was future-proofed to accommodate the long-term goal. Over 200 million passengers annually once all phases are complete. No corner of this site was spared from overachievement. The cargo facilities were built to rival dedicated freight airports, with massive warehouses and high-speed loading systems constructed at breakneck pace. The runway system, built across 4 phases, was designed not only for volume but for wind, direction optimization, weather resilience, and operational efficiency that could outpace even the world's most established airports. Drainage was a particular challenge, given the area's geography. Massive culverts and underground reservoirs were constructed to manage rainwater and prevent flooding, a vital concern in a place where the sea is never far and the weather can turn swiftly. Even power and data lines were installed with redundancy and scalability in mind, buried deep and routed through protected channels to safeguard against both overload and sabotage. When construction crews finally handed over the keys, what they left behind wasn't just an airport. It was a piece of infrastructure that looked less like a public utility and more like a declaration carved into the earth. The sheer act of building it, under such tight deadlines, across such difficult terrain, and on such a colossal scale, stands as one of the great modern feats of engineering. It's not just what was built, it's how it was done. Quickly, relentlessly, and without blinking in the face of impossible complexity.
South of McCormick Place, and stretching toward the edge of Lake Michigan, one of Chicago's largest proposed redevelopment megaprojects is planned on land long isolated from surrounding neighborhoods. The Bronzeville Lakefront project is a multi-phase, mixed-use development centered on the former Michael Reese Hospital site, representing a major attempt to reconnect Bronzeville to the lakefront through large-scale construction and infrastructure investment. The project area encompasses roughly 48 acres, bounded by 31st Street, 43rd Street, Lakeshore Drive, and the Metro Electric Rail Corridor. For decades, the site was dominated by the Michael Reese Hospital campus, which was demolished in the early 2010s following the city's unsuccessful bid for the 2016 Olympic Games. Demolition and site clearance marked the first major construction phase, removing dozens of buildings and leaving one of the largest undeveloped parcels on Chicago's lakefront. After demolition, the land remained largely vacant while planning efforts evolved. The Bronzeville Lakefront vision emerged as a long-term redevelopment framework rather than an immediate construction project. The master plan proposes millions of square feet of new development, including residential buildings, office and research space, institutional facilities, hotels, and retail. The scale places it firmly among the most ambitious mega projects proposed on Chicago's South Side. Infrastructure construction is central to the project's feasibility. The site requires new internal street grids, utility systems, and stormwater management infrastructure before vertical construction can occur. Because the land sits near the lake and adjacent to major transportation corridors, flood resilience and drainage engineering are critical components. Planned construction includes elevated building pads and modern stormwater detention systems designed to reduce runoff into Lake Michigan. One of the most significant proposed elements is a life sciences and innovation campus intended to anchor early development phases. This component would include laboratory buildings, research facilities, and office space designed to attract medical and biotech institutions. These buildings are expected to be among the first vertical structures constructed once infrastructure work advances, establishing employment density before residential build-out accelerates. Residential construction is planned to follow in multiple phases. The master plan allows for thousands of housing units, including a mix of market rate and affordable housing. Buildings are expected to range from mid-rise to high-rise, with height transitions designed to integrate with surrounding Bronzeville neighborhoods. Construction sequencing is intended to spread residential delivery over many years to match demand and financing availability. Transportation access is a major planning driver. The site is adjacent to Lakeshore Drive and served by the Metro Electric line, with future improvements expected to enhance station access and pedestrian connectivity. Proposed construction includes new pedestrian bridges, improved crossings, and internal bike and transit infrastructure to reduce reliance on cars and better integrate the development with nearby communities. Unlike many downtown megaprojects, Bronzeville Lakefront places heavy emphasis on public space construction. Plans include new parks, plazas, and lakefront connections intended to extend recreational access southward. These spaces are expected to be built incrementally alongside private development, requiring coordination between public agencies and private developers. Timeline projections for Bronzeville Lakefront extend well into the 2030s. Early infrastructure and anchor projects are expected to define the first major construction phase, followed by successive waves of vertical development. Full build-out has always been envisioned as a multi-decade effort rather than a single construction cycle, reflecting both the size of the site and the complexity of funding and approvals.
On the eastern edge of San Francisco, where rusted cranes once loomed over a forgotten stretch of shipyard, the Pier 70 redevelopment is one of the city's most ambitious megaprojects currently under construction in 2026. This historic industrial zone, nestled between the Dogpatch neighborhood and the bay, is being transformed into a vibrant waterfront community, one that blends housing, jobs, public parks, and restored heritage structures into a single cohesive district. The construction underway this year marks the most active phase of the project to date, with key milestones approaching as the site charges toward completion in the early 2030s. As of 2026, multiple parcels across Pier 70 are under simultaneous construction. Residential towers are climbing skyward, with the first phase of housing expected to be completed by 2027. These buildings will deliver nearly 1,100 homes in their initial stage, 25% of which are reserved as affordable housing. Construction crews are also working on major infrastructure upgrades across the site, including new streets, transit corridors, pedestrian paths, and shoreline protections to guard against sea level rise. The heart of the mega project is its connection to the past. Pier 70's redevelopment in 2026 doesn't erase its history, it builds on it. Several historic buildings are being restored and repurposed. These include old machine shops and steel foundries that once supported the shipbuilding industry. In 2026, many of these structures are undergoing seismic retrofitting and interior renovations to be converted into arts venues, retail hubs, and office space for design and tech firms. The goal is to preserve the gritty industrial character of the site while making it usable and vibrant for a 21st century city. Public space is a major focus of the construction effort in 2026. Over 9 acres of parks and waterfront access points are being built across the site. The highlight will be the large central green, an expansive park framed by restored industrial sheds and framed by views of the bay. As of this year, grading, drainage, and landscaping are underway, with full park openings projected for 2028. These open spaces are being built to double as climate infrastructure, designed to absorb stormwater, manage heat, and protect the site from flooding. In addition to housing and public amenities, the commercial component of Pier 70 is actively rising. Office buildings tailored to life sciences, technology, and creative industries are under construction now, with tenants expected to begin moving in by 2027-2028. These buildings are designed with flexibility in mind, featuring adaptive floor plans, outdoor terraces, and energy-efficient systems. Construction in 2026 is focused on delivering the first phase of these workspaces, helping to establish Pier 70 as an employment hub linked directly to the city's evolving economic base. The location is also a key asset. In 2026, construction crews are coordinating with transit agencies to enhance connections between Pier 70 and the rest of the city. Muni lines, bike lanes, and pedestrian links to the nearby Dogpatch neighborhood are all part of the ongoing infrastructure work. There's also future planning underway to accommodate ferry service, which would further connect the development to the regional transit network. When fully completed in the early 2030s, the Pier 70 redevelopment will deliver over 2,000 housing units, 2 million square feet of office and commercial space, 9 acres of parks, and over 300,000 square feet of retail, cultural, and community uses. But in 2026, it's the construction activity that defines the project. Foundation work, steel framing, historic preservation, and shoreline transformation all unfolding simultaneously.
Rather than rising from untouched land, the new Miami-Dade airport emerged through one of the largest continuous airport reconstruction programs ever undertaken in the United States, transforming Miami International Airport into what is effectively a rebuilt megastructure operating in real time. Miami International Airport sits west of downtown Miami and functions as the primary global aviation gateway for South Florida and Latin America. By the late 1990s, the airport's original mid-20th century terminals, roadways, and airfield systems were no longer capable of handling projected passenger growth, new aircraft sizes, or modern security requirements. Miami-Dade County responded by launching a long-term capital improvement effort, commonly referred to as the airport's New Airport Program, a reconstruction on the scale of a greenfield build while maintaining daily operations. The centerpiece of this transformation was the North Terminal Development Program, a multi-billion-dollar mega project that replaced large portions of the airport's aging infrastructure. Planning began in the late 1990s, with construction starting in the early 2000s. The program consolidated multiple older concourses into a single, linear terminal complex designed to improve passenger flow, security processing, and aircraft operations. Construction involved complete demolition of outdated concourses, utility corridors, and support buildings, followed by new foundations, structural frames, and terminal shells built adjacent to active runways and taxiways. This required phased construction sequencing to keep aircraft movements uninterrupted. New terminal structures were built using long-span steel and reinforced concrete systems capable of supporting large wide-body aircraft gates and high passenger volumes. The North Terminal was developed in multiple phases. Early phases focused on airside infrastructure, including new taxi lanes, aircraft parking aprons, and fuel hydrant systems. Subsequent phases delivered passenger processing spaces, including ticketing halls, security checkpoints, baggage handling systems, and customs facilities. The first major sections opened to passengers in the mid-2000s, with full substantial completion achieved in the early 2010s. A critical component of the new airport construction was the installation of an automated people mover system connecting the terminal to remote rental car facilities and parking structures. This required elevated guideways, stations integrated into terminal buildings, and control systems installed above active roadways. The people mover significantly reconfigured landside access to the airport. The reconstruction extended beyond terminals. Miami-Dade County invested heavily in runway rehabilitation and expansion, including pavement reconstruction, lighting upgrades, and drainage improvements. Taxiway geometry was modified to accommodate larger aircraft, such as the Airbus A380 and Boeing 777. These airfield works were completed incrementally over many years, often overnight, to avoid disrupting flight schedules. Cargo infrastructure was also rebuilt as part of the airport's mega-project evolution. New cargo buildings, cold storage facilities, and access roads were constructed to support Miami's role as a major freight hub for perishable goods. These upgrades aligned with parallel mega-projects at Port Miami, reinforcing the county's logistics network. Security and resilience upgrades formed another major construction layer. Post-9/11 requirements led to reinforced terminal layouts, expanded security screening zones, and hardened building systems. Mechanical, electrical, and plumbing systems were replaced or upgraded to modern standards, including redundant power supplies and advanced fire protection. Flood mitigation and drainage improvements were incorporated to address Miami's climate and storm exposure. The timeline of the new Miami-Dade Airport build spans more than a decade. Major construction activity peaked between roughly 2004 and 2012, with continuous smaller projects extending beyond that period. By the early 2010s, the airport had effectively transitioned from a mid-century facility into a modern aviation megastructure, capable of handling tens of millions of passengers annually. Within the broader context of Miami's biggest mega projects, the airport reconstruction stands alongside developments such as the Port of Miami Tunnel, Brickell City Center, and large-scale transit investments. Unlike vertical mega projects, the airport rebuild was horizontal and systemic, requiring coordination across aviation operations, federal agencies, contractors, and airlines. On Chicago's South Branch of the Chicago River, a new sports and urban development mega project is being proposed that would add a purpose-built soccer stadium to the city's expanding list of large-scale construction efforts. The new Chicago Fire Stadium, planned as part of the broader The 78 development, represents a significant shift in how professional soccer infrastructure is integrated into Chicago's urban core. The project centers on the construction of a soccer-specific stadium for Chicago Fire FC, designed to replace the club's current use of Soldier Field. The proposed stadium would seat approximately 22,000 to 25,000 spectators, aligning with modern Major League Soccer standards that prioritize compact design, fan proximity to the field, and operational efficiency. The stadium is planned to be fully enclosed on all sides, with a roof structure intended to improve acoustics and weather protection while maintaining open sight lines to the surrounding cityscape. The site is located on a long vacant 62-acre parcel south of Roosevelt Road, historically used as rail yards and industrial land. This area has been undergoing years of environmental remediation and infrastructure planning. The stadium would occupy a portion of the land designated for entertainment and civic uses within the 78 Master Plan, a larger mixed-use mega project that includes residential towers, office buildings, research facilities, and riverfront public space. Construction for the stadium has not yet begun, but the proposal outlines a privately financed project, primarily funded by the team's ownership group. Estimated costs range in the hundreds of millions of dollars, reflecting not only the stadium itself, but also associated infrastructure such as utility connections, riverwalk improvements, and transit access enhancements. The intent is to minimize direct public subsidy while leveraging existing city investments already committed to the 78's foundational infrastructure. From a construction standpoint, the stadium would involve deep foundation work due to the site's industrial past and proximity to the river. Soil stabilization, pile driving, and flood mitigation measures would be required before vertical construction could begin. The building structure is expected to combine reinforced concrete lower levels with a steel superstructure supporting seating tiers and roof elements. Prefabrication is likely to be used for seating bowls and roof components to reduce on-site construction time. Timeline projections place the earliest possible start of major construction in the mid to late 2020s, contingent on final approvals, design completion, and coordination with adjacent developments. If approved on an accelerated schedule, construction would likely take approximately 2 to 3 years, suggesting a potential opening near the end of the decade. This would align the stadium's debut with later phases of the 78's build-out, rather than its initial residential and office towers. The stadium's integration into Chicago's transportation network is a key planning component. The site is within walking distance of existing CTA rail lines and metro services, and future transit enhancements tied to the 78 could further improve access. Pedestrian bridges, expanded sidewalks, and riverwalk connections are anticipated as part of the surrounding public realm improvements, allowing the stadium to function as a year-round anchor rather than a single-use venue. From an urban planning perspective, the project marks a departure from the city's previous approach to large sports facilities. Instead of placing the stadium on the urban periphery or adapting an existing multi-purpose venue, this mega project embeds a professional sports facility directly into a dense, mixed-use district. This allows stadium operations to support nearby businesses, housing, and public spaces, extending economic activity beyond match days. The proposed stadium also addresses long-standing operational challenges for Chicago Fire FC. Soldier Field's size, configuration, and scheduling constraints have limited matchday atmosphere and revenue potential. A dedicated stadium would provide full control over scheduling, sponsorship integration, and fan experience, while also reducing operational costs associated with renting a large NFL venue.
Not every airport begins with a blank slate. Some rise out of the chaos of overburdened infrastructure. and others, like Shanghai Pudong International, are built with foresight, planned from the ground up to handle a future that had not yet arrived. In the 1990s, Shanghai's existing airport, Hongqiao, was bursting at the seams, hemmed in by the city's explosive growth. The answer wasn't to expand within, it was to build outward, toward the coast. What followed was a high-speed campaign to reclaim land from the East China Sea and erect one of the most strategically engineered air hubs in Asia. Construction began not on solid land, but on soft, low-lying tidal flats. These coastal mudlands presented a serious engineering challenge. To establish a stable foundation, workers undertook an enormous land reclamation effort. Millions of cubic meters of sand and earth were dredged, compacted, and layered to form a platform strong enough to carry the weight of runways, terminals, and supporting structures. To prevent long-term subsidence, a real threat in such terrain, engineers employed deep piling techniques and advanced geotextile stabilization systems. It wasn't just about laying the groundwork. It was about making sure that groundwork could last for decades under the pressure of non-stop air traffic. Once the land was stabilized, Pudong's first phase was fast-tracked into reality. The master plan was modular and scalable, with future expansion built into the DNA of the project. Terminal 1, with its long, linear design, was constructed to handle the rising wave of international traffic, linking China's financial hub with the global economy. The roof structure, supported by a forest of sleek steel columns, was engineered for both visual lightness and structural strength, while large spans of glass maximized daylight without sacrificing thermal performance. Inside the terminal's shell, kilometers of electrical, plumbing, fire protection, and air handling systems had to be embedded with flawless precision. Every conduit and junction coordinated across dozens of contractors and engineering teams working simultaneously. The initial runway system was laid with equal attention to durability and volume. High-performance concrete was poured in long, uninterrupted sessions to create seamless surfaces for large-bodied aircraft. Drainage systems had to be designed not only for heavy rainfall, common in the region, but also for the complex water table beneath the reclaimed land. Pump stations, culverts, and storm channels were embedded into the very bones of the airport to ensure operations could continue during typhoons or seasonal flooding. Every phase was built with layers of redundancy, reflecting an understanding that resilience wasn't optional, it was foundational. As Shanghai's international profile soared, so did the scale of Pudong's ambitions. Terminal 2 was added in a massive expansion that more than doubled capacity, echoing the architectural language of the first terminal while integrating newer materials and systems. This phase included another runway, part of a broader plan to maintain aircraft flow without bottlenecks, and an underground transit network linking terminals and remote facilities. Construction crews worked in tandem with aviation authorities to ensure that all additions complied with evolving international standards, from runway safety zones to advanced baggage screening systems. The most striking construction achievement in later phases was the satellite concourse system. Gigantic structures linked by underground automated people movers. These satellite buildings weren't just appended, they were engineered to function as high-capacity extensions of the terminals, with full customs, immigration, and boarding infrastructure integrated underground and vertically. Building these while the airport remained fully operational required phased rollouts, nighttime shifts, and relentless coordination to avoid disrupting flight schedules. Tucked just south of downtown Los Angeles, Exposition Park has always been a place of ambition, home to world-class museums, the LA Memorial Coliseum, and the beating heart of the city's cultural and sporting life. But what's unfolding there now isn't just an upgrade. It's a full-scale transformation, timed to align with the arrival of the 2028 Olympic Games. This is the Exposition Park expansion, and it's one of the most concentrated, multi-layered megaprojects happening anywhere in the city. We're talking about more than 100 acres of dense, high-profile development, the kind of space where architecture, infrastructure, landscape, and engineering have to work in seamless coordination, and every inch of it is being reimagined, stitched together into a new kind of urban park, one that blends Olympic-scale sports facilities with civic space, transit access, and cultural presence. At the center of this expansion is the Lucas Museum of Narrative Art, an enormous, fluid, almost spaceship-like structure that defies traditional design logic. Spanning over 300,000 square feet, the building floats above the landscape on concrete pylons, allowing for an uninterrupted park to run beneath it. Engineering that vision into reality meant solving a long list of structural challenges. The museum's form curves and bends with few right angles, requiring a steel skeleton unlike any conventional grid. Every beam had to be custom fabricated. Load paths had to be recalculated from scratch. But that's only one piece. Adjacent to it, new Olympic training facilities are being added in and around the Coliseum, including athlete, housing, high-performance sports labs, and temporary structures built to IOC standards. These aren't off-the-shelf projects. Each facility must meet international competition criteria while being adaptable for post-games public use. That means flexible infrastructure, modular designs that can expand or collapse depending on future needs, and utility corridors capable of serving both a global broadcast event and a local youth sports league. A new mobility hub is also under construction, tightly integrated with the K Line, Crenshaw LAX line, regional bus service, and pedestrian corridors linking USC, the Natural History Museum, and BMO Stadium. This isn't just about moving people. It's about rethinking access. Engineers are embedding smart traffic systems, ADA upgrades, secure bike lanes, and crowd flow modeling to handle Olympic-scale surges without overwhelming local streets. Then there's the landscape itself. More than 14 acres of new green space are being carved into the existing grid, with bioswales, permeable pavement, and stormwater recycling systems hidden beneath sculpted terrain. Everything is dual purpose. That shaded plaza? It's also an emergency egress route. That rolling hill. It's backfilled over a utilities corridor with seismic isolation joints. Every tree and trail was designed not just for beauty, but for function, cooling microclimates, guiding crowds, and managing runoff during rare but intense LA storms. Beneath the surface, the engineering complexity continues. Utility upgrades, electric, water, fiber, gas, are being laid out like a circulatory system for a future-proof urban core. Crews had to dig and trench with surgical accuracy, often working just inches away from existing structures that couldn't be moved or shut down. Phasing the construction without interrupting events at the Coliseum or the Museum District meant round-the-clock scheduling, heavy prefabrication, and just-in-time delivery logistics.
Stretching through the heart of Central Florida, the I-4 Ultimate project in Orlando represented a massive reconstruction and modernization of one of the state's most heavily traveled interstate corridors. The scale of this infrastructure initiative, spanning 21 miles, required an extraordinary application of highway engineering, traffic management, and structural design, all executed under live traffic conditions. The goal was not merely to widen the interstate, but to reconfigure it entirely to improve traffic flow, safety, and long-term capacity, incorporating express toll lanes, new interchanges, and updated overpasses. The initial phase of work focused on utility relocation and right-of-way clearing, including the removal of outdated bridges, underpasses, and surface roads. Utility coordination was especially complex given the corridor's urban setting. High-voltage transmission lines, water mains, gas pipelines, and fiber optic conduits were identified, surveyed, and in many cases rerouted through newly constructed utility corridors. Horizontal directional drilling and jack-and-bore methods were used extensively to install new conduits beneath active roadways without disrupting surface traffic. One of the hallmark features of the project was the addition of 4 managed express lanes in the center of the existing interstate. To construct these, engineers had to widen the footprint of the corridor and build new median support structures while maintaining the existing traffic lanes. This required extensive temporary shoring, phased traffic shifts, and the use of movable barrier systems. The new lanes were constructed with concrete pavement sections over a stabilized subbase and geotextile reinforced subgrade to support long-term heavy vehicle use. Bridges were a major component of the reconstruction effort, with over 100 new or rebuilt bridges included in the project scope. These ranged from short-span box girder structures to complex multi-level flyover ramps. Precast concrete beams were fabricated off-site and delivered during off-peak hours to minimize traffic disruption. Each bridge's foundation system was engineered to match local soil conditions, typically involving driven steel H-piles or drilled shafts. Bearing pads, expansion joints, and shear connectors were meticulously installed to ensure long-term durability and thermal movement capacity. The project's interchanges were completely redesigned to eliminate weaving and improve vehicular throughput. One of the most complex interchanges was the one at State Road 408, which required stacking multiple levels of traffic lanes, supported by tall piers and connected through sweeping curved ramps. Special seismic joints and post-tensioning systems were used in some of these long-span ramps to meet structural integrity standards and allow for maintenance access. Intelligent transportation systems were integrated throughout the corridor, including overhead gantries with dynamic message signs, cameras, and electronic toll collection systems. The express lanes were outfitted with barrier separation and entry-exit gates, spaced strategically to manage congestion. All ITS components were wired into a centralized traffic operations center, allowing for real-time monitoring and incident response.
There are airports that simply connect cities. And then there's Denver International, an airport that feels more like a myth, wrapped in fog, conspiracy, and raw, undeniable scale. Set against the jagged silhouette of the Colorado Rockies, DN isn't just an air hub. It's a riddle in concrete, steel, and prairie wind. From the moment you approach, you realize this place is different. The terminal roof rises like a row of white peaks, a canvas of fabric stretched into spires that mimic the mountains beyond. It's both architectural poetry and functional design, a nod to the natural world in the middle of a high-tech frontier. But behind the beauty lies a beast of logistics and ambition. Denver International is the second largest airport in the world by land area. Spanning over 50 square miles, it's larger than Manhattan. That space isn't just empty fields, it's a calculated investment in the future. Room to grow. Room to reimagine what an airport can be. When DEN opened in 1995, it did so after delays, budget overruns, and more than a little controversy. It replaced the old Stapleton Airport, not because Denver needed a slightly better facility, but because it needed to think bigger, radically bigger. At the time, few could have predicted how essential that gamble would become. Today, with air traffic climbing and cities swelling, That oversized footprint now looks like foresight. Operationally, it's a marvel. The runways, 6 in total, are set wide apart, allowing simultaneous takeoffs and landings in nearly any weather. This efficiency is crucial in Denver's unpredictable climate, where snowstorms can whip in with little warning. Beneath the surface, a vast tunnel system once built for an ambitious, but famously flawed, automated baggage system still snakes its way below ground. A reminder of how pushing boundaries doesn't always go smoothly. Yet what truly sets Denver apart isn't just the infrastructure, it's the atmosphere. This airport breathes mystery. From strange murals to the giant blue horse sculpture at the entrance, complete with glowing red eyes, Den has become a magnet for conspiracy theories and urban legends. Secret bunkers, underground facilities, coded art. It's all part of the lore. Whether you believe any of it or not, there's no denying the airport has a presence. But look past the shadows, and you'll see something else. A living symbol of Denver's evolution. The airport isn't just a pit stop between coasts. It's a launch pad into the American West. It connects the Rockies to the world, fuels the city's economic engine, and anchors Colorado's global reach. And it does all of that with an eye on what comes next. Den is currently in the midst of multi-billion-dollar expansions, new gates, modernized terminals, and advanced security systems. It's shedding some of its 90s skin and stepping boldly into the 21st century. But even as it transforms, that original ambition, that sense of scale and audacity, still lingers in the wide-open airfields and endless walkways.
Set amid the subtropical lowlands of Central Florida, the construction of the Walt Disney World Resort in Orlando represented a pioneering feat of engineering, site development, and logistics management on an unprecedented scale. Spanning over 40 square miles, the transformation of this expansive and largely undeveloped land into a fully functional entertainment and hospitality complex required not only creative vision, but also advanced technical planning across multiple disciplines, including civil engineering, structural systems, utilities, transportation, and geotechnical stabilization. The first major task undertaken was the extensive site preparation, as much of the land was composed of wetlands, swamplands, and pine flatwoods with limited load-bearing capacity. To make the site suitable for large-scale construction, engineers employed a vast drainage and land reclamation strategy. A series of canals, retention basins, and stormwater management systems were excavated to control the water table and direct excess runoff into purpose-built bodies like Bay Lake and the Seven Seas Lagoon. This required dredging operations, the installation of culverts, and the construction of pump stations to regulate flow in both flood and drought conditions. Foundational work across the resort faced challenges due to the high water table and soft underlying soils. To ensure structural stability, deep foundations such as driven concrete piles and auger cast piles were commonly used, especially beneath heavy buildings like resort hotels and amusement park infrastructure. For lighter structures, engineers used preloading and surcharging techniques to compact the subgrade. In certain areas, soil cement stabilization and geotextile reinforcement were added to increase load distribution and prevent long-term settlement. Perhaps the most iconic aspect of the site's infrastructure was the creation of the so-called utilidor system beneath the Magic Kingdom. Rather than being true underground tunnels, these service corridors were constructed at the original ground level. The rest of the park was then built atop a massive earthen berm created by the spoil from the lagoon dredging. These utilidors house all the park's essential support systems, including electrical cabling, water distribution lines, HVAC systems, waste disposal, and logistics corridors. allowing for seamless and invisible operations above. Utility infrastructure was designed with redundancy and scale in mind. Independent water treatment and wastewater facilities were constructed on-site to handle the large demand. Extensive power distribution networks, including multiple substations, were integrated into the landscape to provide uninterrupted electrical supply across the property. Chilled water systems were installed to provide air conditioning via underground piping loops, using centralized plants that optimize energy efficiency. Transportation planning also played a critical role. A multimodal network was engineered to facilitate the movement of guests and goods, including monorail lines, ferryboat systems, internal bus loops, and service roadways. The monorail system, composed of elevated precast concrete beams supported by reinforced concrete piers, was built with precise tolerances to ensure smooth travel and high passenger throughput. All stations and transfer points were constructed with ADA, compliance and capacity planning in mind, utilizing modular concrete platforms, steel framing, and covered walkways. The scale and complexity of building the Walt Disney World Resort in Orlando set new benchmarks for themed development and remains a masterclass in how multidisciplinary engineering can be applied to create not just buildings or rides, but an entire controlled and immersive built environment engineered to handle millions of visitors each year with both efficiency and spectacle.
In 2026, one of the most visually dramatic megaprojects under construction in San Francisco is the redevelopment of the Potrero power station site. Rising on a stretch of industrial waterfront in the Dogpatch neighborhood, this 29-acre site is being transformed from a rusting relic of the city's energy past into a dense, mixed-use community that blends housing, innovation space, and public waterfront access. After decades of inactivity and pollution, the area is now filled with active construction, with multiple buildings rising around the preserved smokestack that once powered large parts of San Francisco. This year marks a turning point in the project's timeline. Key infrastructure has been installed, roads are taking shape, and vertical construction is advancing on several residential and commercial buildings. The first wave of occupancy is expected in 2027, while full build-out of the project will continue into the early to mid-2030s. In terms of current construction activity, 2026 is the first year where the scale and form of the new neighborhood are clearly emerging on the skyline. The development plan includes over 2,600 residential units, 20% of which are designated as affordable, along with office space, labs, retail, cultural venues, and a massive new waterfront park. In 2026, at least 4 parcels are under active construction, with cranes on site, facades being installed, and streetscape work underway to connect the site to the surrounding Dogpatch and Pier 70 developments. The power station's original brick boiler house is being stabilized and preserved to eventually be converted into a centerpiece public building, part of a broader trend in the project to mix new construction with industrial heritage. The Potrero power station site has long been one of the last undeveloped pieces of San Francisco's southeastern waterfront, and in 2026, it's becoming a key node in a chain of megaprojects that are physically reconnecting the city to its shoreline. The public realm is a major focus of the construction, with waterfront promenades, plazas, and parks currently being graded and landscaped to open in stages beginning in 2028. These green spaces are designed not just for beauty, but for resilience, integrated with sea level rise protection and sustainable stormwater systems. A major portion of the site is also being prepared for future commercial tenants in the life sciences and advanced technology sectors. In 2026, lab-ready office space is under construction, with leasing expected to begin the following year. These facilities are a core part of the megaproject's economic impact, offering high-tech employment opportunities and reinforcing San Francisco's role in the Bay Area Innovation Corridor. Construction in 2026 is being carried out with strict environmental oversight, given the site's legacy as a fossil fuel power plant. Soil remediation, groundwater treatment, and air quality monitoring are ongoing as each new section of the site is prepared for development. This adds complexity, but also makes the transformation more significant, turning a brownfield into a 21st century neighborhood that meets the city's housing and sustainability goals. When fully completed, the Potrero Power Station will be a dense, transit-rich waterfront extension of the city, blending over 6 acres of parks, thousands of homes, and over 1 million square feet of office and retail space into a single, cohesive community. In the landscape of San Francisco's 2026 megaprojects, it stands out for its mix of industrial past and future potential. Every structure rising here is part of a deliberate effort to reshape how cities evolve, from polluted infrastructure into vibrant, livable places. Amid the swirling dust and sun-baked plains of northern Egypt, where the echoes of antiquity still hum beneath the surface, a different kind of monument began to rise in the 20th century. Not one, carved from stone, but cast in concrete and steel. Cairo International Airport was conceived as Egypt's primary portal to the modern world, a replacement for the aging Al Mazah Airport that could handle the soaring demands of commercial aviation in a capital rapidly expanding in population, influence, and ambition. From its inception, the project was steeped in logistical complexity, shaped by the challenges of working in a desert environment while tethered to the ambitions of a globalizing era. The early phases of construction focused on establishing the core infrastructure that would serve as the foundation for decades of layered growth. Located northeast of central Cairo, the site had to be fully excavated, graded, and serviced with basic utilities in an area that, at the time, lacked deep infrastructure. Massive swaths of earth were moved, and early work involved laying vast concrete aprons and taxiways capable of withstanding the punishing heat and seasonal extremes of the region. The soil conditions, arid and loosely compacted, required specialized engineering techniques to ensure long-term stability. Foundations were reinforced with deep footings and treated aggregate layers to mitigate shifting and cracking under the relentless Egyptian sun. Terminal construction began with a modular approach, an intentional strategy designed to facilitate future expansion without disrupting operations. Terminal 1, known in its early form as the Old Airport, was built with broad, open-plan halls supported by a reinforced concrete frame and long-span steel beams. The design prioritized resilience over aesthetics, focusing on airflow, structural simplicity, and load-bearing efficiency. Glass curtain walls and shading systems were introduced to reduce thermal gain while still allowing for natural light, crucial in a location where daytime temperatures often soared. As aviation volumes increased, the terminal underwent multiple expansion campaigns, each requiring retrofitting older structures with newer systems for baggage handling, ventilation, and fire safety, all while keeping the terminal partially operational. The addition of Terminals 2 and 3 marked a significant evolution in construction philosophy. Terminal 2, originally completed decades ago, eventually underwent a complete overhaul to bring it in line with international standards. This reconstruction was a feat of surgical engineering. The original frame was selectively demolished, and new sections were grafted into the existing structure. Contractors worked in tight, active zones, reinforcing aging concrete, integrating new seismic protections, and threading miles of electrical, plumbing, and HVAC lines through spaces never designed to hold them. Terminal 3, on the other hand, was a clean slate, constructed from the ground up as a state-of-the-art facility to accommodate wide-body aircraft and higher passenger volumes. Its frame was built from high-strength concrete and a steel roof truss system, supporting a terminal footprint that included dual-level departure and arrival flows, jet bridge systems, and a matrix of automated luggage belts built into a multi-tiered substructure. Beyond the terminals, Cairo's runways demanded careful engineering. Laid in parallel orientations to optimize wind handling and maximize simultaneous movements, the runways were constructed with high-durability concrete overlays and embedded lighting systems for all-weather operations. Groundwork involved excavation and subgrade stabilization across thousands of linear meters, requiring constant calibration to maintain level grading and load-bearing integrity. Runway expansions had to be synchronized with radar installations, air traffic control upgrades, and expanded taxiway systems to manage growing traffic without compromising safety or efficiency. Meanwhile, auxiliary construction, parking decks, maintenance hangars, fuel farms, and cargo facilities developed in parallel. Each support system required its own logistical plan, from fuel pipeline installations and fire suppression systems to cold storage zones for cargo handling. The cumulative effect was a sprawling, highly compartmentalized aviation complex whose every square meter had to be engineered for durability, redundancy, and heat resilience. Few megaprojects embody Cold War secrecy and Arctic engineering like Norway's Olavs Vern submarine base, an underground naval facility tunneled directly into a mountain just outside Tromsø, north of the Arctic Circle. This hidden fortress was conceived at the peak of NATO's strategic concerns in the North Atlantic and took decades of planning, excavation, and military coordination to bring into reality. Construction began in the late 1960s, driven by NATO's urgent need for a hardened naval base in Scandinavia to monitor and counter Soviet submarine movements in the Norwegian and Barents Seas. Olavs Vern was designed from the outset to support both surface vessels and nuclear-powered submarines, offering them a completely secure and concealed operations hub within Norway's extreme northern geography. Engineers excavated over 25,000 cubic meters of solid granite to build the complex. The core of the facility is a massive internal dry dock, 300 meters deep into the mountain, capable of housing several submarines at once in total secrecy. Entry was via a camouflaged sea tunnel, nearly invisible from aerial or satellite reconnaissance, allowing vessels to slip in and out without detection. The entire complex was built with one purpose: survivability under sustained military threat. The mountain provided natural shielding against conventional and nuclear attacks, while internal blast doors and reinforced corridors added additional layers of protection. The dry dock could be sealed completely from the outside, and pressure systems maintained stable conditions even in the event of chemical or nuclear fallout. Inside the mountain, over 13,000 square meters of operational space was carved out and fortified. This included command and control rooms, crew quarters, repair workshops, fuel and weapons storage, and climate-controlled chambers for advanced sonar and electronic systems maintenance. The facility was fully self-sustaining, with independent power generators, freshwater reserves, and secure communication lines linking it to NATO's command network. Construction was carried out under extreme environmental conditions. Winter temperatures regularly plunged below freezing, and the surrounding fjords presented major logistical challenges for transporting materials and machinery. Specialized tunneling equipment had to be shipped in and adapted for Arctic rock conditions, while crews worked in shifts around the clock to meet strategic deadlines. The base was built not only to hide submarines, but to actively service and rearm them for extended missions. Fuel depots were constructed with double reinforced walls, and weapon storage areas were shielded against electromagnetic pulse effects. The internal rail systems moved torpedoes, spare parts, and equipment deep within the base without reliance on outside handling. Everything was streamlined for rapid turnaround under wartime conditions. Strategically, Olavs Vern gave NATO forward positioning capabilities near Russia's northern fleet bases on the Kola Peninsula. Submarines stationed there could shadow Soviet movements, gather acoustic intelligence, and act as a deterrent in a theater where control of the Arctic sea lanes could shape the outcome of a global conflict. The level of investment in the base reflected the military significance of the High North. At its peak, Olavs Vern was staffed by hundreds of naval personnel, including engineers, weapons technicians, and communications officers trained for cold weather warfare. It remained one of NATO's most classified assets throughout the Cold War, largely unknown even to much of the Norwegian public. What makes Olavs Vern unique among submarine bases is not just its concealment, but its integration with the landscape. Unlike visible dry docks or floating depots, this installation was invisible until you were inside it. It combined Arctic geography, naval warfare, and fortress-level engineering into one seamless warfighting platform. Even after its deactivation in the early 2000s, the facility's infrastructure remains intact, ready, if necessary, to be reactivated for a new era of geopolitical tension in the Arctic. As competition over the polar regions intensifies, Olavs Vern stands as a reminder that military megaprojects are often not just about weapons, but about geography, silence, and the ability to vanish beneath stone. Few structures have ever emerged from the ground with such poetic symmetry and brutal precision as Beijing Daxing International Airport. Born from an urgent need to relieve pressure from the overcrowded Beijing Capital Airport, Daxing was never going to be just a supplement. It was designed from the start as a symbol of China's ascendancy in aviation, infrastructure, and high-speed construction. The plan was staggering. A brand new airport built from scratch in less than 5 years, capable of handling tens of millions of passengers annually, and anchored by one of the most architecturally complex terminal structures ever attempted. The site chosen was flat and unremarkable farmland in the Daxing district, but it was about to become the nucleus of a new economic corridor. Before a single column could rise, thousands of workers, engineers, and machines had to transform an empty stretch of land into one of the most interconnected transportation hubs on Earth. At the heart of the project was the terminal itself, a sweeping, starfish-like structure that pushed the boundaries of spatial design. The challenge wasn't just to make it beautiful, but to make it brutally efficient. A central node with 6 extending arms meant that all gates could be reached with a maximum walking distance of just a few hundred meters, radically improving passenger flow. But constructing such a layout meant tackling extreme technical complexity. The roof alone is an engineering spectacle, a vast, undulating canopy of steel and glass that required precision assembly down to the millimeter. Dozens of custom-fabricated joints, expansion mechanisms, and modular support systems had to be installed in perfect harmony to accommodate both structural loads and seasonal temperature swings. Massive steel trusses, each weighing dozens of tons, were hoisted into place in synchronized operations that resembled the choreography of a space mission more than a traditional building site. Underground, an entirely separate world was being constructed. Beneath the terminal, construction crews carved out a multi-level labyrinth of tunnels, utility corridors, and high-speed rail links, some of which were laid concurrently with the rising terminal structure above. Timing and sequencing were everything. Sections of the underground rail platforms had to be sealed and reinforced, even as excavations were still ongoing elsewhere. The integration of subway lines, intercity trains, and future maglev systems meant that crews were building not just for today's capacity, but for a future where the airport would sit at the heart of a mega-regional transport network. Every slab of concrete, every steel beam underground, had to be laid with total synchronization with the structural demands above ground. And all of it had to happen without pause. Construction logistics on this scale verge on the surreal. Materials were delivered with military precision, steel from multiple provinces, glass from high-performance manufacturers, and prefabricated components trucked in across thousands of kilometers. On-site coordination was controlled through centralized digital platforms, utilizing BIM, building information modeling, to track every component, system, and timeline in real time. Massive cranes, custom-built for the height and reach required, moved like slow, mechanical dancers across the worksite, while armies of workers labored beneath them in shifts that rarely stopped. The workforce was huge, tens of thousands at the peak of construction, yet safety records remained among the best in the region due to a combination of strict protocols and smart monitoring systems. Environmental considerations, too, were built directly into the construction process. Entire stormwater retention systems, solar panel arrays, and thermal insulation technologies were integrated from the beginning, not tacked on as afterthoughts. The runways, of which multiple were built in parallel, were laid with advanced materials designed to withstand decades of use and extreme weather conditions. Drainage systems were buried deep and wide, designed to handle Beijing's summer rains without compromising operations. Fuel systems, baggage conveyors, HVAC installations, all were constructed with a mind toward redundancy, modularity, and long-term resilience. The G Line, formerly known as the Orange Line, was never designed to stay the same. From the beginning, it was a workaround, a bus rapid transit route built in place of a rail line due to funding constraints and political compromise. But over time, its ridership and strategic location forced the city to rethink what it could be. Now the G Line is undergoing a major transformation, an infrastructure upgrade project spanning the entire 18-mile corridor through the San Fernando Valley, pushing the limits of what bus transit can do in Los Angeles. The goal is simple: increase speed, capacity, and safety. But executing that goal has required deep and complex engineering interventions at nearly every point along the route. One of the most critical changes is the installation of a state-of-the-art signal priority and preemption system. Unlike traditional traffic signals that respond to fixed timers or limited sensors, this system actively clears intersections ahead of approaching buses, reducing delays and allowing for smoother flow across dozens of street crossings. Another major element is the construction of grade separations, rail-style overpasses and underpasses, at the busiest and most delay-prone intersections. Key locations like Sepulveda Boulevard, Van Nuys, and others are being excavated and rebuilt with concrete bridges and undercrossings to allow buses to pass through without ever stopping for cross-traffic. These structures require complex retaining wall systems, traffic rerouting, and in some cases, full reconstruction of local street infrastructure around the new grades. To support higher frequency service, the corridor is being outfitted with new power systems, bus-only lanes resurfaced with heavy-duty concrete, capable of supporting constant vehicle weight, and upgraded station platforms. The existing asphalt guideway, originally built to mimic light rail tracks in layout, has been deteriorating under the strain of articulated buses. Rebuilding it requires full-depth removal and replacement with reinforced concrete slabs, tied into a subsurface drainage system to prevent water intrusion and pavement shifting over time. Platform upgrades go beyond aesthetics. Stations are being lengthened to accommodate longer, higher-capacity buses and future electric models. Each platform is being raised and re-leveled to allow for near-zero gap boarding, speeding up passenger flow and improving accessibility. Integrated electrical conduits and utility vaults are also being installed during construction to prepare for future overhead charging systems as the fleet transitions to full electric. A core part of the upgrade involves upgrading the actual vehicle fleet. Metro is phasing in battery electric buses with larger passenger capacities, regenerative braking systems, and onboard diagnostics. These buses weigh more than their natural gas predecessors, which has direct implications for bridge loading, braking distances, and pavement wear. Engineers had to revisit structural tolerances across the entire corridor, from culverts and embankments to turning radii and clearance zones, to ensure long-term durability under heavier rolling stock. Fiber optic lines are also being laid alongside the corridor to support real-time monitoring. Everything from vehicle location, signal interaction, passenger load, and environmental data will be fed into Metro's central control center. This data will be used not just for dispatch, but to dynamically adjust signal cycles and reroute in case of emergencies. Drainage systems along the G line were never built for current-day storms. As part of the upgrade, culverts are being expanded, bioswales are being added to medians, and runoff channels are being lined with concrete and fitted with sensors to monitor flow levels during heavy rain. All of this is necessary to prevent trackway flooding and preserve the subgrade from erosion.
Long before Miami's skyline signaled its rise as a global city, the expansion of Port Miami and its tunnel interchanges quietly re-engineered the region's economic foundation through one of the most consequential infrastructure megaprojects in the county's history. Port Miami, located on Dodge Island in Biscayne Bay, underwent a coordinated expansion program during the late 2000s and early 2010s, aimed at transforming the port into a post-Panamax global trade hub. This effort combined portside construction, navigational improvements, and highway-grade tunnel interchanges into a single integrated mega project. The goal was to remove physical, maritime, and logistical constraints that limited cargo growth while separating freight movement from downtown Miami's surface streets. One of the earliest and most critical construction components was the deepening of the port's main navigation channel. Prior to expansion, the channel depth restricted access for larger container vessels. Dredging operations began in the early 2010s and involved removing millions of cubic yards of material from Biscayne Bay to achieve a depth of approximately 50 to 52 feet. This work was completed in 2015, timed to coincide with the expanded Panama Canal, allowing Port Miami to receive fully loaded post-Panamax container ships for the first time. On NAS, Dodge Island itself, extensive terminal reconstruction took place in parallel with dredging. Older cargo berths were demolished and rebuilt with reinforced concrete wharves capable of supporting heavier cranes and higher container loads. New gantry cranes, some of the largest in the world at the time of installation, were erected on reinforced rail systems embedded into the key structure. Yard areas were regraded and paved to accommodate automated container handling equipment and higher stacking densities. Utility infrastructure beneath the port was also rebuilt. This included new electrical substations, stormwater drainage systems, fuel distribution lines, and communications networks designed to support modern terminal operations. These upgrades were completed incrementally to avoid disrupting ongoing cargo and cruise activity, requiring phased construction zones across the island. The landside component of the expansion centered on the Port of Miami Tunnel and its highway interchanges, which together form the port's primary freight access system. Construction of the tunnel began in 2010 and was coordinated directly with port expansion schedules. The tunnel consists of 2 submerged roadway tubes connecting Dodge Island to Watson Island, bypassing downtown Miami entirely. Equally significant were the tunnel interchanges themselves. On the mainland side, major roadway reconstruction was required to tie the tunnel directly into Interstate 395 and Interstate 95. This involved building new elevated ramps, retaining walls, and transition structures capable of handling heavy truck volumes at highway speeds. Existing roadways were demolished and realigned, with traffic maintained throughout construction using temporary detours and phased lane shifts. On the port side, Dodge Island underwent extensive reconfiguration to integrate tunnel portals with internal port circulation. New access roads were built, grade separations installed, and security checkpoints relocated to streamline truck movement. These changes allowed cargo vehicles to enter and exit the port without crossing cruise passenger traffic, significantly improving operational efficiency and safety. The tunnel excavation itself was completed in 2013, but the interchange construction and systems integration extended into 2014. The full tunnel and interchange system opened to traffic in August 2014, marking a major milestone in the port expansion timeline. From that point forward, thousands of trucks per day were rerouted away from downtown Miami streets and directly onto the interstate network. The expansion program also included rail infrastructure improvements. Port Miami's on-dock rail connection was rehabilitated and reactivated, linking the port directly to Florida East Coast railway lines. Track upgrades, switching yards, and loading areas were constructed to enable intermodal freight transfer, reducing dependence on trucking for long-haul cargo movement. In the context of Miami's biggest megaprojects, the Port Miami expansion and tunnel interchanges differ from high-rise developments by operating as a systems-level transformation. The project did not create a single landmark structure, but instead rebuilt the physical processes that allow the city to function as a logistics hub. Its completion aligned with other regional megaprojects, including airport cargo expansion and downtown redevelopment, forming an interconnected infrastructure network.